Welcome to this set of tutorials about the auditory system. We'll begin with this session speaking about peripheral mechanisms that are important for transferring the energy in the environment in the form of sound waves into electrical signals that will be processed by the brain. These topics will relate to several of our core concepts in the field of neuroscience. We'll be speaking of the complexity of the brain. We will introduce a new core concept with this session, and that is that the brain makes it possible to communicate knowledge through language. So while this session is not explicitly about language, certainly any discussion of the auditory system would not be complete without at least some mention of human speech. And, well, of course, it's our brain that brings us here this evening and endows us with a natural curiosity to understand how the world works. I have two learning objectives for us this evening. First, I'd like for you to be able to describe the biomechanics of sensory transduction in the middle and inner ear, including the important concept of tonotopy that is established in the basilar membrane. I want you to be able to characterize the neurophysiology of sensory transduction in auditory and vestibular hair cells. Now, our focus is on the auditory system, but as you'll see, the very same mechanisms apply to the sensory transduction apparatus of the hair cells in the vestibular system, which will be a topic for a tutorial that we will come to very shortly. Well, I want to begin with providing you an overview of the auditory system and auditory function. And we're just going to step right through this. If you don't want to read as I'm talking, then just listen. But otherwise, I want to put the words in front of you because these next two slides really provide a bulleted framework for our discussion of the auditory system. Well, let me begin by just stating for you what is the challenge in auditory function. Well, the challenge really is to transduce energy that comes in the form of sound waves. Well, this is what the auditory system does. It transduces sound waves into distinct patterns of neural activity that are then integrated with other sensations and motivations to guide behavior. So, once again, in a sensory system, we need to consider the process that begins with sensory transduction and ends with the guidance of behavior. Now let's see how the auditory system accomplishes these goals. First of all, sound waves are collected and amplified by the physical structures that comprise the external ear and the middle ear. And these structures transfer that energy to neural elements that are present in the inner part of the ear. The biomechanical properties of the inner ear then decompose complex sounds, such as the sound of my own voice, into sinusoidal components, so that the component frequencies, their amplitude, and their phase can then be encoded in the firing of the receptor cells. What comes next is the establishment of a principal form of mapping that we see in the auditory system, which is called tonotopy, or the mapping of auditory tone. So in the inner ear, and then throughout the rest of our central processing stations, tonotopy is preserved. The story continues in the brainstem. What we see is that auditory information is first processed and divided into several parallel pathways in the brainstem. Some of these pathways will compare the signals derived from the two ears, and this allows for the localization of sound in auditory space. Within the brainstem, there are centers that relay information up to the midbrain, and there an important integrative center is the inferior colliculus. So the inferior colliculus of the midbrain, in turn, sends projections to the auditory division of the thalamus, a region called the medial geniculate complex. And then, as we've seen in our other sensory systems, the specific thalamic division that receives this ascending sensory information projects to the cerebral cortex. and therefore defines what we will call the primary auditory cortex. So within the auditory cortex, information is received from the thalamus, and of course it's further processed and further elaborated, and the more complex aspects of sound are represented, including the sounds of human speech. With that broad overview of the functions of the auditory system behind us, now let's consider each step along the way, beginning with the nature of sound. Well, sound comes from spherical pressure waves of vibrating air molecules, and one simple way to induce such vibrations is with a tuning fork. Well, I happen to have a tuning fork with me here, and if I just tap it appropriately, I can hear the vibrations of the tines at a frequency of 440 cycles per second, or 440 hertz. Perhaps you can hear that as well. Of course, another way to produce that kind of a tone would be with a musical instrument. So I happen to have my guitar with me, and here's the tone that I just produced by the tuning fork. Well, of course, if my guitar is in tune, that is. That should be very close to the frequency of 440 hertz. Here's another tone, which I'm particularly fond of for some reason. That is the tone of an F sharp, which is just below 440 hertz. As I've set in motion the tines of the tuning fork or the string of my guitar, what I've done is created spherical pressure waves. And these pressure waves can be characterized really in terms of three fundamental properties. The amplitude, which has to do with the depth of this modulation, of the contraction and expansion of these pressure waves as they travel through air. So amplitude is what we interpret as the intensity of the sound. Another parameter has to do with the pitch or the frequency of the wave. That is, what is the distance between one peak and another, or one trough and another? So the frequency is what we interpret as the pitch of that tone. And as sound is perceived by the two ears which sit on either side of my head, another aspect of this spherical pressure wave that's traveling through space becomes important. If we imagine sound coming from one side of our location or another, then there will be a temporal shift or a phase difference between the waveform that's encoded in one ear compared to the other. So a difference in phase becomes an important property of sound as we perceive it in our two ears that becomes encoded in the firing patterns of auditory nerve cells. Now, sounds in the environment and the sounds that we ourselves produce in speech were simply single frequencies of sound that could be characterized by a simple sine wave. Well, perhaps the job of auditory processing would be quite simple. But then again, perhaps life would be a little less interesting. Now, this F sharp by itself makes a rather pleasant tone, but I'm rather fond of it in the context of a chord that is more complex and includes other tones. And even human speech is incredibly complex. It seems like it might be a rather simple auditory stimulus, but there are all kinds of frequencies with varying pitch and varying phases depending upon how these different temporal frequencies are combined as we make different speech sounds. So human speech presents a great example, just as appreciating a complex pattern of tones in music presents a great example of the challenge faced by the auditory system. So now let's talk about how this energy in the environment actually is collected and then transduced by the structures of the ear and ultimately converted into electrical signals that travel into the brainstem. So just a quick bit of anatomy of the human ear. So we see a very nice illustration here of the anatomy of the external, the middle, and then the inner portions of the human ear. And the external ear looks a little bit odd, odd in some of us more so than others, but its structure has a particular purpose. What this external ear is doing is it's collecting sound frequencies from our environment. And the shape of this external ear, including the pinna and the concha, is acting to collect those frequencies that are particularly germane to our environment and especially to the sounds that we ourselves produce. So our external ear gathers sound and allows that sound then to be focused and concentrated as the sound pressure waves enter the external auditory meatus on their way to the tympanic membrane, which we find on the medial edge of the external auditory meatus. These structures also filter sounds and are very useful in helping us localize sounds in the environment. We become attuned to those sounds that are specifically filtered and funneled down into this external auditory meatus. Next, let's turn our attention to what we find in the middle region of the ear. So if we look more closely at this region, what we find is the tympanic membrane, which is a diaphragm that sits at the junction of the external and the middle ear. And just on the medial side of the tympanic membrane, we find three of the most exquisite bones of the human body that one can discover. These are called ossicles, the ossicles of the middle ear. They are the malleus, the incus, and the stapes. And they articulate in a particular way to achieve a biomechanical leverage over the sound energy that's being transmitted from the vibrations of the tympanic membrane. In fact, there's about a 200-fold amplification of energy from the impact of that sound energy on the tympanic membrane to the piston-like action of the stapes pressing against the inner ear. The stapes makes contact with a region that we call the oval window, and it vibrates in and out. And again, about a 200-fold amplification of energy occurs through the way the biomechanics of these ossicles align and transmit their energy as they articulate. And next, let's have a look at the inner ear. The inner component of the ear is comprised of a beautiful set of membranous canals that run through the petrous temporal bone. There are essentially two divisions of this structure. There's an auditory division, which is found here, and it's represented by a snail shell-like structure called the cochlea. And there is a vestibular division, which we'll come to in a subsequent tutorial, that includes a set of sensory structures that are sensitive to the movements of the head. So for sound, the cochlea is the structure of interest. This cochlea really has a twofold purpose. It has a biomechanical function and a neural function. The biomechanical function is to decompose complex sounds into their component frequencies. The neural function then is to transduce this mechanical energy into neural signals that are then communicated through the auditory nerve and into the brainstem. Now let's look more closely at the anatomy of the cochlea. So cochlea is a Greek word that means snail, and it refers to this coiling that we see resembling the shell of a snail. And if we were to look at a cross-section through that cochlea, what we would see is a set of membranous channels. In fact, we see two large channels that appear to be bisected right through the middle. And if we look carefully at that structure of bisection, we see yet a third channel. So here's an enlarged view over to the right, and what we find are these large fluid-filled channels. And this partition that separates those two large channels has buried within it a smaller channel and a set of exquisite structures that are present on the base of this partition. So just a bit of nomenclature here. So the coiled structure that we find is called the cochlea, and the partition that we see is called the cochlear partition. And then the base of this cochlear partition is a structure that we call the basilar membrane. The basilar membrane has a roof. You may remember from the neuroanatomy of the midbrain that another word for roof in brain anatomy is tectum. So there is a roof over this structure called the tectorial membrane. So there's a basilar membrane below and a tectorial membrane above. And making contact between the basilar membrane and the tectorium are the sensory cells. And these sensory cells are called hair cells. From the apical surface of these hair cells are cilia, and these cilia make contact with the tectorial membrane that forms the roof over this epithelium that sits on the basilar membrane. The cochlear partition is innervated by the peripheral processes of nerve cells that sit in a ganglion that spirals around the turns of the cochlea. So this ganglion is called the spiral ganglion, and it's the ganglion, or it's the location of the cell bodies that grow the auditory component of the eighth nerve. The peripheral components of these spiral ganglion cells grow out and make contact with the basal region of the inner hair cells. We also find an additional collection of hair cells called outer hair cells. And these outer hair cells really are not sensory cells at all. Rather, they serve an important biomechanical function where they actively tune the vibrations of this structure as the basilar membrane articulates with the tectorial membrane. And then lastly, I'll highlight this inner channel that runs through this cochlear partition. It's called the scala media, and it contains a very different kind of fluid than what's found in these other larger spaces, the scala vestibuli and the scala tympani. And as we'll see, the fluid in the scala media is critical for the process of sensory transduction in the inner hair cells. One more point to make about these channels that run through the cochlea. As the spirals of the cochlear reach the apex, the scala vestibuli and the scala tympani actually come together around the tip of the basilar membrane, right here at the apex of the cochlea. So there's actually continuity in the fluids that are present in these two large channels that run the length of the cochlea. So I'd like to now give you a broad overview of the function of this part of the inner ear. So we have a little region right here that's called the oval window, and this oval window is the site where the stapes makes contact with the inner ear. So you'll recall that the stapes is the most proximal of those three inner ear ossicles, and it functions like a little piston that moves back and forth, providing pressure on the inner ear at the level of the oval window. And as the stapes bulges into that oval window, pressure waves are transduced into the fluids that run in the scala vestibuli and the scala tympani. And these fluids then are conducted along the entire length of the cochlea. From this site of inward protrusion here in the oval window, and then eventually that pressure is relaxed with an outward bulge at the round window. And along the way, there are vibrations that are set up along this cochlear partition, from the base of the cochlea all the way up through its apex. These waves of pressure that are conducted through the fluids that run through the cochlea then will cause a vibration to happen within this cochlear partition. And that vibration then will cause a mechanical deflection of those tiny cilia at the tips of the hair cells. And this will be key for the transduction of this energy into electrical signals. Now what I'd like to do next is to talk about the tuning properties of this basilar membrane. And one convenient way to do it will be to uncoil this cochlea and stretch it out flat and have a look at the properties that exist across the length of that basilar membrane. So that's what we've done here. This is a representation of the human cochlea. So here's our stapes pressing back and forth against the oval window. Here's the round window where that pressure is commensurately relieved. And now I think we can better appreciate how pressure waves might travel from the oval window out to the round window with this point of continuity at the tip of the cochlea, which is called the helicotrema. So on the superior side we have the scala vestibuli, on the inferior side the scala tympani. And what the movement of the stapes does then is sets up a traveling wave that causes the basilar membrane to vibrate up and down as these waves are conducted throughout the cochlea. And it's this movement of the basilar membrane, specifically the movement of the basilar membrane against the tectorial membrane, that causes the hair cell cilia to move one way and then the other. Now, as we look at this cochlea unwound, we need to appreciate some of the biomechanical properties of the basilar membrane that allow for that important function to be performed, that is, the decomposition of complex sound into component frequencies. So near the base of the cochlea, the basilar membrane is considerably thicker and stiffer than what we find at the apex. At the apex of the cochlea, the basilar membrane is broader and it's much thinner than what we find at the base. And this gradation that we find between the base of the cochlea and the apex allows the basilar membrane to map out in a smooth progression tone, with high frequencies being represented near the base of the cochlea, where the basilar membrane is much stiffer and it will vibrate best at high frequencies, compared to the apex of the cochlea, where the basilar membrane is much more pliable and vibrates best to low frequencies. So if we looked at, for example, positions 1 and 2 here near the base, we find higher frequencies that give rise to the greatest amplitude of vibration, whereas positions 6 and 7 now vibrate best with greatest amplitude with low frequencies of stimulation. Now, in addition to these biomechanical properties that establish this important principle of tonotopy or frequency mapping in the auditory system, there are active mechanisms that involve the outer hair cells that fine-tune the way this coupling works between the basilar membrane and the tectorial membrane. If we look then at this organ of Corti in the cochlear partition, what we see is contact between the tectorial membrane and this organ of Corti, this sensory epithelium. And the contact is in the form of these stereocilia that grow out of the apex of these hair cells. These outer hair cells, they're innervated, but they're actually innervated by axons that have an efferent signal. So we can think of them as being motoric in nature. The motor is actually in the hair cell itself. So what these hair cells do is they can contract and extend. And as they do so, they change the stiffness of their contact with the tectorial membrane. And this active mechanism then allows for the vibrations to be fine-tuned by the central nervous system. Meanwhile, the inner hair cell is innervated by sensory fibers that have grown out of the spiral ganglia that sits near the axis of rotation of this cochlea. And these sensory endings then will receive the electrical signals that are generated here in the inner hair cells. So let's now see how this all works. So as traveling waves run through the scala vestibuli around the helicotrema into the scala tympani, this cochlear partition begins to vibrate up or down. And because of the pivot points of these two membranes are offset relative to the center of the cochlea, what we find is a shearing force develops as this cochlear partition rises upward and then recesses downward. This shearing force deflects the stereocilia at the tips of these hair cells first in one direction and then in the opposite direction. So with each up and down cycle, there is a wagging back and forth of these stereocilia at the apex of the hair cells. And that movement of these cilia will open and close ion channels that allow ions then to enter the tips of these stereocilia and generate graded potentials in the inner hair cells. So let's now talk about how sensory transduction actually works at the tips of these hair cells. So, as I mentioned earlier, there is a third channel that sits in this cochlear partition, and it is quite special. It has a different kind of media in it compared to what we find in our scala vestibuli and our scala tympani. In those two larger channels, the solution that we have there is called perilymph. And perilymph is very similar to the solution that bathes most of the cells of our body. It has a relatively low concentration of potassium, and as you now know quite well, within nerve cells, potassium is concentrated to quite high levels. Now, the scala media is really distinct in this respect. It has very high levels of potassium. This endolymph is enriched in potassium because of the activity of cells in a highly vascularized structure that has extremely high metabolic activity. It's called the stria vascularis, and this is an epithelium that secretes potassium and concentrates it within this scala media. Now, why is that relevant for sensory transduction? So here is an inner hair cell, and its stereocilia are protruding off the apical surface of the organ of Corti, that sensory epithelium. And at the very tips of these stereocilia are potassium channels. And the potassium channels from one stereocilium to the next are connected with a spring-like protein called a tip link. And what that protein does is it connects a gate that is on the extracellular side of this potassium channel from one stereocilia to the tip of an adjacent stereocilia. And as a result, as these stereocilia wave in one direction, the tip links are stretched and that transduction gate is opened. And when the gate is opened, then potassium ions can rush down their concentration gradient, because remember, potassium is concentrated to very high levels here in the scala media. So as potassium enters through these potassium channels at the tips of the stereocilia, the hair cell will depolarize. And a graded potential is established in that hair cell with the influx of potassium. That potential eventually opens up voltage-gated calcium channels that exist on the sides of these hair cells. So now, not only does potassium enter through the apical surface of the hair cell, now calcium rushes in through the basolateral aspects of the hair cells. And as calcium enters, then a calcium-dependent exocytosis of synaptic vesicles occurs along the basal region of the hair cell. Essentially, neurotransmission occurs. A neurotransmitter then is secreted from these vesicles and makes contact with receptors at the peripheral end of the spiral ganglion processes. So this afferent nerve here then is receiving synaptic connection from this inner hair cell. And with the release of transmitter, binding to receptors, ionotropic channels open up, and cations rush in to that afferent nerve terminal, and an action potential is generated that may then propagate into the brain. Now, what I've described for you is what happens when the stereocilia are deflected in a particular direction towards the longest stereocilium. That's the deflection that puts stress on the tip link, pulling open that transduction gate, allowing for potassium to flood into the stereocilium. Well, I mentioned that these cilia will move back and forth with the upward and downward phases of deflection of the basilar membrane. As these stereocilia then relax back and are bent in the opposite direction away from the tallest stereocilium, then the stress on those tip lengths is relaxed, and the transduction gate can then close over the top of the pore of the channel. So the movement of these stereocilia allow for the cyclical opening and closing of this transduction gate. And one can imagine then what would happen to the membrane potential. The membrane potential would rise, would depolarize as the stereocilia are deflected towards the largest stereocilium, and then the membrane potential would fall or hyperpolarize as those tip links are now relaxed, the gates close, and potassium no longer rushes in. So what we see here is with displacement of the stereocilia on the apical surfaces of the hair cell, there is the cyclical depolarization and hyperpolarization that happens as the stereocilia are moved back and forth or up and down in the direction that is parallel to the axis of orientation from smallest stereocilium to largest stereocilium. And if one were to move these hair cells in the orthogonal direction, that is rather back and forth from the axis of shortest to longest, then what we would find is basically no change in membrane potential, because we would neither be stretching those tip links nor would we allow them to relax back. So if we were to look down on the hair cell, what we would find is that there is a very special type of stereocilium called a kinocilium. We're actually born with this, but for most inner hair cells, the kinocilium is lost in life. Nevertheless, there is this gradient from shortest stereocilium to tallest stereocilium that is present next to where the kinocilium once was. And so if we move these stereocilia along this axis from smallest to longest and back and forth, that's where we find the greatest amplitude of oscillation in membrane potential. If we were to move in the orthogonal axis, basically we wouldn't be stressing out those tip lengths, and consequently we would have no change in membrane potential. Now let's look at how good these hair cells actually are at faithfully reproducing the cycles of pressure that cause these traveling waves to be set up along the length of the basilar membrane. If we stimulate these hair cells at a frequency of, let's say, 300 hertz, 300 times a second, we see a beautiful modulation in the membrane potential of that hair cell. And as we advance the frequency, what we find is that these hair cells can faithfully represent the temporal aspects of the stimulus all the way up through at least a kilohertz. So here's 1,000 hertz, a kilohertz of modulation. And we can still detect a beautiful sinusoidal type cycle in the membrane potential of that hair cell. But once we get above about a kilohertz or so, we begin to lose the ability to follow the frequencies of that pressure wave. And that's a pretty amazing accomplishment, that we can record with fidelity the movements of these hair cells up to more than 1,000 cycles per second. But at some point, we just can't operate as quickly as the energy in the environment. But we can still encode that energy because there is a DC component to the response. That is, the hair cell on average becomes depolarized, even though the modulations, the AC component, now basically vanishes as we get above about 2 kilohertz. So as we continue to increase in pitch, in the frequency of the stimulus, we can still activate hair cells in an appropriate zone of the basilar membrane. But we can no longer produce an AC component of modulation that faithfully captures the temporal dynamics of the stimulus. Let's back up for just a moment, and I'll remind you then that at the basal region of the hair cell, we find synaptic vesicles. So for an action potential to be fired in the afferent nerve fiber, neurotransmission must take place. And a sufficient depolarization to activate voltage-gated sodium and potassium channels must be generated here in the afferent nerve fiber. Now, I'd like to invite you to pause this tutorial and look at your tutorial handout for a couple of web links to some really excellent resources that have been generated that summarize these aspects of auditory physiology that relate to these peripheral structures found in the middle and the inner ear. The first is an animation found on the website that supports our textbook, and you can navigate there on your own, or you can simply click the link in your tutorial notes. The second is really one of my favorite animations in all of neuroscience. It's just a wonderful tour through the biomechanics of the basilar membrane created by one of the real giants in the field of auditory neuroscience, Dr. James Hudspeth. Well, he didn't actually do the animation, but he commissioned it and oversaw the production of this really beautiful presentation that I think really makes very clear how the basilar membrane can decompose complex sound, even Bach's staccato and fugue, into component frequencies that are then encoded in the oscillations of membrane potential in the hair cells that happen to be at each location along the length of the basilar membrane. So please go watch these two animations and then come back and we'll conclude this tutorial. Okay, well, I hope you enjoyed that. I know I sure did. Now, I want to just conclude by talking about sensory coding in the auditory nerve. If we look at the cycles of stimulation that are going to be transduced by our hair cells, what we'll find is that for any given axon in the auditory nerve, there is a barrage of action potentials that can be recorded with some predictable temporal relationship to the stimulus. In this case, it's a fairly low frequency stimulus, and what we see is a faithful and highly reproducible barrage of action potentials that is elicited at a particular phase relationship to the stimulus. If one were to look across a family of axons within the auditory nerve and plot the firing rate that is observed for any given frequency of stimulation, what we would be able to do is to plot a tuning function for that axon. And so what we're looking at here is a plot of the intensity of the stimulus that's necessary to elicit action potential firing in the axon. And what we find, for example, this axon that is plotted here in purple above, is that the threshold is lowest at a particular frequency. meaning it takes less amplitude of modulation to elicit action potential firing in that axon. Well, a different axon is going to have a different best frequency, and so on. So here we have examples from 6 different axons recorded in an auditory nerve, and they all have a different best frequency. And this figure is illustrated in a way that is meant to organize these best frequencies across that tonotopic map that we find established in the basilar membrane. And sure enough, the auditory afferents that innervate the base of the cochlea are going to have their best frequency near the higher range of what can be heard and transduce. So in this case, this gold-colored plot is showing the best frequency around 10 kilohertz for this particular axon that's innervating the base of the cochlea. Meanwhile, way at the other end of the cochlea, here is an axon that's innervating some domain of the basilar membrane that's closer to the apex, and we find a much lower best frequency, much less than 1 kilohertz. Well, I should have made this point earlier, but for us humans, we're sensitive to sound over a range from about 20 hertz to about 20 kilohertz. So if we were to be very close to the base of the cochlea, that's roughly where we would find our maximum frequencies that could be represented across our basilar membrane, whereas out near our helicotrema, near the apex of the cochlea, that's where we would find the lowest range of frequencies found. Okay, well, in our next tutorial, I'd like to discuss with you how this information that is generated here in the inner ear is processed in the central nervous system. So I'll see you back for that discussion. Well, welcome back to this second tutorial on the auditory system. In this tutorial, I'd like to talk to you about central processing of auditory stimuli in the brainstem and in the forebrain. Again, we are considering some of the very complex aspects of sensory processing that takes place within our special sensory systems. And the circuitry that does this job is by and large genetically determined, and it provides the foundation for all that we hear. These systems acting together make it possible for the brain to communicate knowledge through language, one of the highest achievements of the human brain. And of course, again, we wouldn't be here together having this discussion were it not for the curiosity that our brain gives us about how systems such as this actually work. I have 2 learning objectives for you in this tutorial. I want you to be able to identify and to discuss the neural mechanisms for localizing sounds in space. This is a very important aspect of the job that the auditory system does. And then I want you to be able to discuss more broadly the organization of the auditory cortex, which really points to a second major role for the auditory cortex in our brains, and that is the understanding of human speech. So let me again step through an overview of auditory function with you. Well, auditory function begins when sound waves are collected and amplified by the physical structures in the external and middle ear. And these sound waves then are transferred to the neural elements in the inner ear. There, the biomechanical properties of the inner ear decompose sound waves from their complex frequency spectrum to sinusoidal components, so that their component frequencies including other aspects of their energy envelope, including their amplitude and their phase, can be encoded in the firing of the receptor cells. Those receptor cells are found in the inner part of the ear, and at that station of auditory processing, we see for the first time the establishment of a kind of a map, a frequency space. This is called tonotopy. So tonotopy is established in the inner ear, and it's preserved in each of the central processing stations that we will be discussing in this session. We're going to spend some time talking about the brainstem here, and in the brainstem, this is where we find auditory information that is divided into parallel pathways. And along those pathways, there are various special functions performed, including a comparison of the signals that are derived from the two ears. And this is critical for the localization of sounds in space. These brainstem centers will process auditory signals in other ways as well, and relay information to the midbrain, to a structure there known as the inferior colliculus. And the inferior colliculus in turn sends projections to the auditory division of the thalamus, a structure called the medial geniculate complex. The auditory thalamus in turn provides input to the cortical division that first receives information about sound, and that's our primary auditory cortex. It's found in the superior aspect of the temporal lobe. This auditory cortex receives this input from the thalamus and processes more complex aspects of sound, including those that are related to human speech and even music and other aspects of our culture that are based in the auditory modality. Okay, well, this tutorial is focused on central processing, so we need to confront some details regarding the anatomy of the auditory pathways. So I have good news and bad news for you. Well, depending upon your tolerance for complex neuroanatomy. Well, the good news is that I am not going to be showing you cross-sections through the brainstem highlighting the location of gray matter and white matter pathways in the manner that we did for the somatic sensory system. These pathways are often not so clear, not so compact. Some of them are, and I certainly could point you to some gray matter structures, but I won't. I will name them, and I will invite you to find them on your own. There are really just a couple that I care for you to be able to recognize because they are significant and discernible in different views of the nervous system, and I'll mention them as we go. The white matter structures, however, I just won't even attempt to show you exactly where they are. Rather, we will be satisfied with the schematic illustration that I'm showing you here from Chapter 13 of our companion textbook. Now, I know the details are small, and you probably can't see them on the screen that you're using right now, so I'm going to break this diagram into two parts, and that way we'll have a better look at each station. And let's begin in the inner ear and recognize that action potentials have been generated now in the peripheral process of our spiral ganglion neurons. And those action potentials very well will propagate back through the vestibulocochlear nerve, the eighth cranial nerve, and then enter the brainstem on the lateral aspect of the junction between the pons and the medulla. Hopefully you will recall the location of that eighth cranial nerve as it connects up with the brainstem. If not, maybe you want to go back and look at one of the earlier video tutorials to remind yourself of exactly where that occurs. Well, the eighth cranial nerve conveys two modalities of special sensation, our auditory sense and our vestibular sense. We'll come back to the vestibular sense in the next tutorial, but for now, let's just isolate our thinking on the auditory component of that eighth nerve. Well, the auditory component enters the brainstem at this lateral aspect of the tegmentum, just below the junction of the pons in the medulla. And what we find is a set of nuclei that seem to form a bit of a cap along the dorsal lateral aspect of the inferior cerebellar peduncle. We call these nuclei the cochlear nuclei. And several divisions can be recognized. I won't worry about those divisions, but I'll just mention that they exist. And this cochlear nucleus then is the first structure to receive the afferent signals that are conveyed to the brainstem from the eighth cranial nerve. The cochlear nucleus has its own circuits that do some measure of processing, and I won't get into that at all. The cochlear nuclei serve an important function of distributing the auditory information to additional brainstem centers that perform their own computations. One of them in the upper part of the pons is called the nucleus of the lateral lemniscus. This nucleus gets input from the contralateral cochlear nucleus, and on that basis it's processing signals that are derived principally from one ear. Now, another very important set of nuclei, also in the pons but now in a more inferior position, are nuclei of the superior olivary complex. And so we find that here, very near the level of the facial motor nucleus. And the superior olivary nuclei are really quite special. They receive input from the cochlear nuclei on both sides of the upper medulla. So here in the superior olive, we have a comparison of signals that are derived from the two ears. I want to come back and talk in more detail about exactly how the divisions of the superior olive assist in the localization of sound based on that comparison between the two ears. But for the time being, let's move on up the auditory pathway. So here is this nucleus of the lateral lemniscus in the superior aspect of the pons that I alluded to earlier, that's mainly concerned with processing monaural signals, or signals derived from just the contralateral ear. Well, the nucleus of the lateral lemniscus and the superior olive, not shown here in this cut through this figure, these structures send input on up into the midbrain. And that's where we find an important integrator of ascending auditory information, the inferior colliculus. Now, you'll recall if we look at the dorsal side of the midbrain, we have these four little bumps or four little hills, which is what colliculus means. There's a superior pair and an inferior pair. The inferior colliculus is the auditory relay that I want you to be able to find and recognize. If I were to ask you, where is the inferior colliculus, I would expect you to say that it is in the dorsal aspect of the midbrain, or the tectum, to be more particular about the term we use for this region of the midbrain. And it's the inferior of the two pairs of small bumps that we find there. Well, within the inferior colliculus, we have the convergence of all of this ascending auditory information. And we still struggle to really understand exactly what the inferior colliculus is doing. But it seems to be the first place in the auditory pathway where a complete map of the auditory world is computed. This includes both the distribution of space in terms of azimuths and also elevation. Well, the inferior colliculus performs a variety of computations that are still subject to ongoing investigation, and we have only a partial understanding of exactly how the different components of the inferior colliculus integrate the ascending auditory information and compute that map of the auditory world. But nevertheless, it happens, and the signals that are processed in that inferior colliculus are then relayed from the midbrain on up to the thalamic nucleus that receives this auditory information. And that nucleus is called the medial geniculate complex of the thalamus. We use this word complex because it's really not a single nucleus. It's comprised of several subdivisions, and those subdivisions then further distribute this auditory information to various targets in the forebrain. So the largest division of the medial geniculate complex grows its axons and sends input into our primary auditory cortex, which is found in the superior plane of the superior temporal gyrus, buried deep in the lateral fissure, which, as you will recall, is the name that we give to the space between the temporal lobe and the overlying operculum formed by the parietal and frontal lobes. So we'll come back and talk in just a little bit about the organization of that auditory cortex. At this point, what I'd like to do is return back down this pathway to the level of the lower pons, and I'd like to talk a little bit about these very interesting computations performed in the superior olivary nuclei that help us to localize the source of sound in space. So there are several subdivisions to the superior olivary complex, and I'd like to talk about two of them, beginning first with a division that we call the medial superior olive. In the lower left of this slide, I have a bit of a photomicrograph that shows you what this medial superior olive actually looks like. This is from a primate brainstem, and this nucleus takes the shape of a spherical ball, and the outline of the ball is roughly about there. And the reason why I'm showing you this Nissl stain is because there's a very unusual distribution of cell bodies within this spherical shape. The cell bodies are all found right along the equator of this ball, and those cell bodies are all lined up in a very characteristic array such that they can extend their dendrites in opposite directions away from that equator. Well, this is the arrangement that is shown schematically in the figure from our textbook that we have in front of us here. And what we see is that along this equator, there is a systematic distribution of interaural latency differences from one end of the medial superior olive to the other. So here's how this works. In the medial superior olive, neurons become precisely tuned to the timing difference between the encoding of sound in one ear and the other ear on the other side of the head, obviously. Now here in this figure we see a schematic representation of this array of cells that we find here across the equator of the medial superior olivary nucleus. And I want you to notice that each neuron here in this medial superior olive receives two sources of input. One source of input is the cochlear nucleus coming from one side, and the other source of input is the complementary cochlear nucleus on the other side of the brainstem. And in order for any one of these cells to fire an action potential, there must be the coincident arrival of the electrical signal causing the release of neurotransmitter from both of these pathways onto the neuron. So when that happens, then the neuron can fire and transmit its signal to its targets. Well, let's take this neuron E, for example, in this illustration. In order for neuron E then to fire, there must be the simultaneous arrival of input from the left ear and the right ear. Well, because of the difference in the path length from the cochlear nucleus on the left side of the brainstem to neuron E compared to the path length from the cochlear nucleus from the right side of the brainstem to neuron E, the only way that inputs can arrive simultaneously would be if the sound source is shifted over here to the left somewhere. So if that sound source is here on the left-hand side, then the activation of the left cochlea is going to occur before the activation of the right cochlea because of the temporal lag in the conduction of that sound wave from the left side of the head to the right side of the head. So even though the path from the left cochlear nucleus to neuron E is longer, with sound present on the left-hand side of the midline, the signal is going to get started in advance on the left side compared to the right side. And with the sound source shifted to the left, neuron E is much more likely then to receive coincident input from both sides of the brainstem. The same basic scenario would apply to each of these neurons that are in a slightly different position along the equator of this nucleus. Finally, on the opposite side of the nucleus, we would find a cell that has exactly the opposite arrangement from what we discussed for neuron E. It has a long path length from the right side, a short path length from the left side. So coincident activation of these inputs to neuron A would require localization of sound over here to the right. So the path length is short to the right ear, long to the left ear, allowing for the longer path length here to be started in advance of the shorter path length. Well, this is really a beautiful system. It requires the precise development of connections that are specifically tuned for delays between the arrival of sound energy on the two sides of the head. And I wish we had time to talk in more detail about exactly how this system develops and how it's tuned up to the environment. But that's a wonderful story that pertains to development and developmental plasticity, which I would invite any of you interested to look up that literature and discover more about that for yourself. So this is the story of the medial superior olive. It encodes the localization of sound in space based on interaural timing differences. Well, there's another division of the medial superior olive that I'd like to tell you about. It's the lateral superior olive, and it encodes information about the location of a sound source based on interaural intensity differences. Okay, so the medial superior olive bases its signals on interaural timing differences, the lateral superior olive on interaural intensity differences. Well, here in this part of the superior olive, the circuitry is just a little bit more complex. There is a second nucleus involved. So here is the lateral superior olive, and the secondary nucleus is a source of inhibitory input to the lateral superior olive. It's called the medial nucleus of the trapezoid body. So here's how this circuit works. Inputs derived from the cochlear nucleus on one side of the brainstem send projections on up to the superior olive. So there are inputs that go directly to the lateral superior olive, causing an excitation of that cell. But there's also collaterals that project across the midline to this medial nucleus of the trapezoid body. Neurons in the medial nucleus of the trapezoid body grow short connections then to the lateral superior olive and function to inhibit that nucleus when activated from the opposite side of the brainstem. So you can imagine what would happen if there were a sound source localized over here just to one side. Let's say this is the left side of the brainstem here. So this left lateral superior olive would be excited and fire at an increased rate, whereas the right lateral superior olive will be inhibited. And that's exactly what is plotted over here to the right-hand side of the figure. We're looking at the output of the lateral superior olive, or just the firing rate of neurons in this structure, relative to the location of the sound source. Now, If the sound source is well to the left side of the head, for example, we would expect the intensity of that sound to be much greater in the left ear compared to the right because of what's called an acoustic shadow that's cast by the head. Basically, the energy will be absorbed on the left-hand side of the head more so than would be transmitted to the right side. Consequently, with a left-sided sound source, we would expect there to be very strong activity in the left lateral superior olivary nucleus, but also strong inhibition in the right superior olivary nucleus. So while activity is quite high with that left-sided sound source in the left LSO, we would expect activity to be just about shut down in the right lateral superior olive, again because of this inhibitory connection via the medial nucleus of the trapezoid body. Now, if we look on the opposite side of the head with a sound source localized to the right, we would expect there to be strong activity in the right lateral superior olive, but inhibition of the left lateral superior olive. So this difference between the activity of the two sides of the superior olivary complex is one means for encoding the location of sound in space based on this intensity difference that arises because of the acoustic shadow cast by the head. Now, with the sound source directly in front of the listener, that sound source would have equal intensity in the two ears. So consequently, the activation of this inhibitory circuit would essentially null out the difference in activity levels across the two sides of the lateral superior olive. Well, the upshot of all of this is that the superior olivary complex of the inferior pons provides a dual means for encoding the localization of sound in space. The medial superior olive encodes the localization of sounds in space based on interaural timing differences, whereas the lateral superior olive encodes the location of a sound source based on intensity differences between the two sides of the head. Well, as we saw earlier, these kinds of signals and others derived from the computations of the superior olivary complex and the nucleus of the lateral lemniscus converge in the inferior colliculus, where a complete map of auditory space is computed for the first time along this pathway, not just the location of azimuths, but also elevations. The inferior colliculus sends relays up to the auditory division of the thalamus, the medial geniculate complex, and from there the medial geniculate complex projects to the primary auditory cortex. And it's about the primary auditory cortex that I'd like to conclude this tutorial. So the auditory cortex is organized into a core region which is surrounded by a belt of higher order auditory areas. That core region is found along the superior aspect of the temporal lobe. And there's a series of transverse gyri that we find on that superior plane of the temporal lobe that are called Heschl's gyri. And typically 2 or 3 of these gyri are where we will find the terminations of the medial geniculate complex of the thalamus. So that's where we would find our primary auditory cortex and the core division, which is illustrated here in blue. So this primary auditory cortex found here on the upper part of the superior temporal gyrus is where we would find a complete representation of the frequencies that are first encoded down in the basilar membrane. So we have a frequency map of our auditory environment established across the modules that comprise this auditory cortex. The more anterior region responds to stimuli that are encoded near the apex of the cochlea, whereas the more posterior region encodes the higher frequencies that are first transduced near the base of the cochlea. And again, surrounding this central core region is a belt of auditory areas that seem to process increasingly complex aspects of auditory information. Of course, one aspect of audition that is very important in this part of the brain is human speech. And some division of this higher order auditory area includes what we call Wernicke's area. So somewhere in this auditory belt region, we have circuits that are essential for understanding human speech, not just the spoken word, but also written human language. We call this region Wernicke's area. This region is named after the German physician Wernicke, or perhaps you prefer the pronunciation Wernicke, who described a series of patients that had damage to this part of the brain. And one consequence of that damage is an inability to understand human speech. So Wernicke's area is often depicted as being present in the posterior aspect of the superior temporal gyrus. However, if you consult with neurosurgeons that actually map out our functional Wernicke's area in the human brain during neurosurgical procedures, we find that Wernicke's area might be distributed over a much broader region that potentially extends into the inferior parietal lobule and all the way anterior near the anterior pole of the temporal lobe. Now, that's not to say that all of this cortex is Wernicke's area, but rather there may be key nodes in a lateral temporal network that are critical for understanding human speech. The job of the neurosurgeon is to identify these key nodes and do his or her very best to avoid damaging them in the course of neurosurgery. So, an illustration such as this that points a leader to one particular region and calls that Wernicke's area is potentially a bit misleading. So I would advise you, if you are ever subject to neurosurgery in your lateral temporal lobe, make sure you have a surgeon that specializes in mapping language in these areas, and please make sure that your surgeon maps your languages, not just the language of the surgeon. There have been famous errors made in these surgical procedures in this part of the brain because a surgeon may not have considered the possibility that there may be different nodes in this lateral temporal network that are essential for understanding speech in different languages. That indeed seems to be the case. Those of you that are multilingual, you may have several important nodes in your network that are critical for each of the languages that you have come to understand. So this is a very complex system. It's more broadly distributed than we once thought, and it's an area of ongoing investigation to understand how this part of the human brain is organized and functions. Another important point to make about Wernicke's area is that for nearly all of us, it's present in the left hemisphere. Those that have a functional Wernicke's area in the right hemisphere are likely to be left-handers. Now, not all left-handers have a right hemispheric dominance for language function. It's just that left-handers are more likely than right-handers to show this opposite pattern of asymmetry. Actually, one idea that has gotten a fair amount of interest is that in left-handers, the pattern of asymmetry is simply more random than what is observed in right-handers, where we very consistently find a left hemispheric dominance for language function. Now, that's not to say that there is not specialization of the right hemisphere with respect to language function. Indeed, there is a region in the right hemisphere that corresponds to what we describe, at least structurally, as Wernicke's area. It may be less critical for understanding language than what is present in the left hemisphere, but it could be quite important nevertheless. One aspect of the right hemisphere that seems to be important in language function is prosody. Prosody refers to the emotional content of speech. Damage to the lateral aspect of the right temporal lobe may lead to impairments in understanding the emotional content of speech. So a person with such an injury may be able to understand the meaning of the words in terms of their semantic content, but might not be able to pick up the nuances of emotion that are present in speech. Not only is language lateralized to the left hemisphere for most of us, but there is also a structural difference between the left and right temporal lobes in this region of this auditory belt cortex. The superior aspect of the posterior temporal lobe is a sort of a flat region that we call the superior temporal plane, or the planum temporale, and it appears to be larger in the left hemisphere compared to the right hemisphere. Consequently, the lateral fissure is longer and straighter in the left hemisphere compared to the right hemisphere, where there's often an upward bend, giving the impression of a shorter lateral fissure in the right hemisphere. Well, that difference that we observe from the outside, we think reflects this difference in the extent of this superior temporal plane in the two sides, with about 2/3 of us having a larger planum temporale in the left hemisphere compared to the right. Now, it had been thought, and perhaps still there's some truth to this, that this asymmetry in structure relates to the asymmetry in function that's associated with language comprehension. However, the fact that the majority of us, somewhere around 97-98% of us, have our functional Wernicke's area in the left hemisphere, whereas only about 2/3 of us have an asymmetry of the planum temporale, suggests that there must be more going on there. Well, one interesting clue as to what might be going on was discovered some years ago when a study was done of planum temporale size in individuals who were musicians, some of whom had this very special ability called perfect pitch. And this is the ability to be able to discriminate tone, or to be able to produce tone of a given pitch, and to know exactly what that pitch is. Well, most musicians, professional or otherwise, don't have this ability, but some do. And at least a cohort of individuals with this special talent, this ability to discriminate and to produce perfect pitch, ended up having a larger asymmetry in their planum temporale region compared to skilled musicians that lack this ability. So there's something about the asymmetry between the auditory regions in the two hemispheres that gives rise to this special talent. And it will be interesting to see if other dimensions of music perception, or perhaps even music performance, might also be related to asymmetries in these parts of the brain. And finally, I'd like to show you just a little bit of data on this point of asymmetry in the region of the auditory cortex, and just highlight some of the specializations that we're beginning to learn about this fascinating part of the brain. As you listen to my voice, there is a greater volume of your left auditory belt region activated compared to your right. So left is greater than right when listening to human speech. And this presumably reflects the specializations that we call Wernicke's area that are manifest in the left lateral temporal lobe. While we listen to environmental sounds, there is virtually no asymmetry in the activation of the two hemispheres, and presumably that reflects the distribution of auditory connections relative to the range of environmental stimuli to which we must respond. Now, music appears to be quite special and perhaps quite different. When we listen to music, what we find is the opposite asymmetry, with right hemispheric activation being significantly greater than left hemispheric activation. In fact, the asymmetry when we listen to music is even greater than the asymmetry that's detected when we listen to human speech, but it's in the opposite direction. And this presumably reflects a broader and more general bias of the right hemisphere towards encoding signals that pertain to human emotion, although that bias is not absolute. So music seems to engage different networks that are lateralized in a distinct pattern compared to those that are being activated right now as you listen to the sound of my voice. Well, I hope you've enjoyed this discussion of the auditory system and this exploration of some of the physiology of these parts of the brain that are so important for our social dynamics as we communicate orally with one another, and so important in the richness of our lives as we experience the environment. Where I am right now, I'm being serenaded by a chorus of toads in a nearby swamp. I've heard the sound of deer and possum in the forest around me, and the occasional call of the owls that are busy hunting their prey here in the darkness of these woods that surround me. Well, that's all been a joy for me to experience. Perhaps you've heard a little bit of that in this audio track on this tutorial as well. Well, I'll leave you with just a little riff on one of my favorite tunes, and hope you enjoy that on your way out. Hello everyone, welcome to a set of tutorials on the structure and function of the vestibular system. In this first tutorial I'd like to speak to you about peripheral mechanisms of vestibular processing, and in the second tutorial we'll talk about the central processes that operate within the brainstem, on up through the brain and even down into the spinal cord, that implement motor commands based on feedback coming from the vestibular system. And then we'll also talk some about how vestibular input is contributing to our broader sense of proprioception, from which our body schema is created in the brain. Now, I'll refer you to our core concepts in the field of neuroscience, as well as our learning objectives that are found at the top of your tutorial notes. Essentially, our core concepts for this session are that once again we're going to be confronted with the complexity of the brain, and you'll come to even more fully appreciate, I think, the fact that the brain is the body's most complex organ. And we will be talking about circuitry that is genetically determined, as well as structure and form. And I think what you should appreciate is how beautifully do form and function go together when we're talking about the functions of the vestibular system. And I hope you appreciated that when we talked about the cochlea as well when we considered audition, but we'll carry that theme onward as we consider the structure and function of the vestibular system. Okay, and our learning objectives are that I want you to be able to describe the anatomy of the vestibular labyrinth. This is what we call the peripheral apparatus that's deep in our temporal bone. And I want you to be able to describe the biomechanics of sensory transduction in both components of the vestibular labyrinth. That would be the biophysics of hair cell transduction in what we'll call the otolithic organs, and then in our semicircular canals. But let's begin with an overview of vestibular function. So you should recognize that the vestibular labyrinth is an extension of the inner ear that is designed to sense the motions that arise from head movements, as well as the inertial effects that are due to gravity. So what do we mean here? Well, as your head is presumably in a fairly stable position right now, there are signals that are due to the force of gravity tugging on our bodies. And these signals are being processed by the vestibular system with respect to a special set of organs that we find within the vestibular labyrinth. So we're going to talk about that. But of course, our heads are often in motion. Mine tends to bob around quite a bit as I speak, I know that. But our heads are in motion, and those motions produce accelerations. Sometimes linear accelerations as we move in one plane of motion or another. We'll see those planes in just a minute, or rotational accelerations. So these are different kinds of ways that we can move our head. Those linear accelerations in the static positions of our head, these are sensed by the otolithic organs, while the rotational accelerations are being sensed by the semicircular canals. And what we'll discover in each component of the vestibular labyrinth are hair cells that do the job of sensory transduction, very similar to the hair cells we described in the cochlea when we talked about audition. So the good news for you is that the mechanisms of sensory transduction are quite similar in the vestibular system and the auditory system. But we'll talk about the biomechanics of these two components of the vestibular labyrinth, and you'll see how the biomechanics really help to explain the sensitivity of these hair cells, even though the sensory transduction is the same. Okay, well, let's continue with our overview then. So vestibular signals are generated in those otolithic organs in the semicircular canals, and then these signals are relayed to integrative centers in the brainstem as well as in the cerebellum. And these signals travel along the 8th cranial nerve and the vestibular component of that 8th nerve. Well, in these central stations, these signals are used to adjust postural reflexes as well as eye movements. So in our next tutorial, we'll talk about the anatomy of how those kinds of motor actions are engaged by vestibular signals. Of course, these vestibular signals also can impact our sense of well-being, our sense of place, our sense of position, and our sense of movement through the environment that is mapped out largely via auditory and visual signals. So these vestibular signals then are going to reach into the parietal lobe, where our spatial awareness is constructed in cognition. So in the parietal lobe, we have our normal sense of orientation in three-dimensional space. This is where this sense is constructed. And should there be some kind of pathology, this is where feelings of dizziness would come from. There are brainstem circuits that are going to be important for that as well, and we'll touch about that in the next tutorial. So what I do want you to understand, though, is what is the fundamental means by which the vestibular signal provides us with a normal sense of position and equilibrium, and what are the conditions that might give rise to abnormal sensations, and how might those be expressed in our bodies. Okay, well, let's move on then and consider the anatomy of the peripheral components of the vestibular systems. But before we explain the anatomy, it's useful to talk about how we move our heads. So, as I illustrated just a moment ago, we move our heads both in linear planes as well as around axes of rotation. So, just to orient you to this figure, so this illustrates the basic planes through which we move, and of course we move through all the planes that are intermediate between them, and we move in rotations around axes that are intermediate between these cardinal axes here. So we can rotate our heads around the x-axis. So this is a rolling type of action. Okay, think of an airplane sort of rolling off to one side. We can change our rotation around the y-axis as if there was an axis going from ear to ear. This is pitch. This is nodding our head forward and then backward. Okay? And then we can turn our head from side to side. So this is a rotation around the z-axis. This is called yaw. So if you're flying in that plane and the plane does this rather disturbing turn left or right, that is movement in yaw. Okay, so those are rotational movements, or rotational accelerations. There can also be linear accelerations in the forward and backward direction in the horizontal plane, or to the left-right direction in that same horizontal plane. There can also be movement up or down, right, like elevator motion. So these are all linear accelerations, and we see those illustrated here as movements along these principal axes that are illustrated. Now, these 6 basic directions or planes of motion are going to be sensed by different components of the VAR vestibular labyrinth. So I want you to, at the end of this tutorial, be able to explain which elements of the vestibular labyrinth are sensitive to each of these kinds of motions. Okay? Well, in order to get there, we need to look at the anatomy of the vestibular system. And what we find is that the vestibular system truly is a labyrinth. It is a set of interconnected canals that arise from the same embryological precursor called the otic placode that grew out the cochlea. So it's not surprising then that our cochlea should be right adjacent to our vestibular labyrinth. So what we find in the vestibular labyrinth is a series of canals. Now these canals are filled with endolymph. So you'll recall from our discussions of the cochlea, endolymph is that fluid that is enriched in potassium ions. So this means that it is more like the solutions that we typically find within cells rather than our typical extracellular fluids. So the canals are filled with endolymph, which is high in potassium and low in sodium. And then surrounding the vestibular membranes is where we find perilymph, which is more like the normal extracellular fluids of the body. That is low in potassium and high in sodium. And just as endolymph was critical for sensory transduction in the cochlea, so will it be critical for sensory transduction here in the vestibular system. So here's another view of our vestibular labyrinth together with the cochlea. So we have our labyrinth over here to the left-hand side and our cochlea here towards the right. And if we just look at the labyrinth now, we see that there are really 2 classes of sensory structures associated with each side of the head, with each vestibular labyrinth. We have a set of otolithic organs, and these are the utricle and the saccule. So together these 2 organs are similar in their histology and their function, but what differentiates them, as we'll see, is the orientation of their sensory elements. Now, in a similar way, our second class of sensory structures are these 3 semicircular canals. So we have a superior canal, we have a posterior canal, and a horizontal canal. Now these 3 canals have very similar mechanisms of biomechanics and sensory transduction. What differentiates them is their orientation within the temporal bone. And that orientation allows them to be sensitive to different kinds of head movement. Now within each of these sensory structures, the semicircular canals and the otolith organs, we find hair cells. So again, these hair cells are going to be similar to what we described in the cochlea, and they provide for the mechanisms of sensory transduction. These hair cells are innervated by the peripheral processes of ganglion cells that are present in a ganglion called Scarpa's ganglion. So we see that here. So there is a set of nerve cells that sit in Scarpa's ganglia that innervate the otolith organs, and then a separate population that supply the central sensory regions in our 3 semicircular canals. So the peripheral process of these cells receives a synaptic input from the hair cell, and the central process then is conveyed along the axons of the vestibular division of the eighth nerve. So let's talk about sensory transduction now in these vestibular sensory structures. Here's a view of a sensory epithelium. This is a view of what we might find in our otolith organs. And what we see is a sensory epithelium with hair cells. And these hair cells are making synaptic connections with the peripheral process of our eighth nerve fibers. The hair cells grow a set of stereocilia, and these stereocilia have a particular axis to the length of the stereocilia, with the longest stereocilium on the side of this very special structure called the kinocilium. And the kinocilium may or may not be present in adult life. It's okay if it's not. It often does degenerate. But what we're left with then is a set of stereocilia that have some sort of directional axis to their orientation, going from the shortest stereocilium towards the longest. And when there is deflection of these stereocilia from shortest to longest, there will be depolarization of the hair cells. And conversely, if we were to have deflection in the opposite direction, from the longest hair cell towards the shortest, we would find hyperpolarization. Okay, so let me remind you as to why that would be. Again, it's very similar to what we discussed for sensory transduction in the cochlea. Once again, we have stereocilia that at their tips have these transduction channels that are permeant to potassium ions. And the gates on these channels are connected one to the next stereocilium by this spring-like protein called a tip link. And as these stereocilia are deflected from shortest to longest, there is a tension that's applied to this tip link protein, and that opens up the transduction gate, allowing potassium to rush into the tips of the stereocilium. Now you remember that the tips of these hair cells are bathed in endolymph, which has very high potassium concentrations, so high that it's even greater than what we find in the cytoplasm. So these very high potassium concentrations allow potassium ions to enter through these potassium channels. They depolarize the hair cell, and that wave of depolarization now spreads down where it reaches voltage-gated calcium channels. These voltage-gated calcium channels open, and calcium rushes into the cell from the fluids that bathe the lateral and basal aspects of this hair cell. And as calcium rises within this hair cell, then in a calcium-dependent manner, there's exocytosis of vesicles at the base of the hair cells and the release of neurotransmitter onto the afferent terminal. This neurotransmitter is probably glutamate, and it's probably binding to receptors like AMPA receptors on the afferent ending of this eighth nerve fiber. And if sufficient glutamate's bound, there could be a generator potential developed there. If sufficient glutamate's bound, then this afferent fiber can depolarize and generate an action potential, and then a signal will be conveyed along the eighth nerve to the brainstem. Now, let me say just a little bit about the orientation of hair cells in our sensory epithelium, because this turns out to be quite important for understanding the function of each of our sensory structures in our vestibular labyrinth. For the otolith organs, what we find are the hair cells are arranged with a certain axis of symmetry that divides the sensory epithelium within each of our otolithic organs. So for example, notice here in the saccule, so this is the sensory epithelium in the saccule. This is called a macula, meaning a spot. So there's a special sensory spot in each otolith organ called a macula. And these arrows here are meant to illustrate the axis of symmetry of the hair cells. Now notice that in the saccular macula, there is an axis of symmetry that sort of runs right down the middle of this structure. And the hair cells are organized from shortest to longest going in opposite directions. So the arrow points towards the longest stereocilium. So this means that if we're going to deflect these hair cells along their axis for depolarization or hyperpolarization, then this saccular macula would need to be rotated essentially along the y-axis, which means the saccular membrane is going to be sensitive to deflection that would either pitch the head in a forward tilt or in a backward tilt. Also, the accelerations up and down that we would experience in an elevator would also be expected to be in line with the orientation of activation that we find here in this saccular macula. Now let's look at the utricle and its macula. Now there is also an axis of symmetry here, and there's a bit more of a curvature to this axis, and what we find are that the hair cells are arranged basically with the opposite kind of polarity. That is, the longest stereocilium is towards the line of symmetry, with the shortest being peripheral to that line of symmetry. Now, this utricle macula is largely in the horizontal plane. Not entirely, there's a little bit of it that curves upward, but it's largely in the horizontal plane, while the saccular macula is largely in the vertical plane. So this means that this utricle macula is going to be most sensitive to linear accelerations that we might make with our head in the horizontal plane. If we were to tilt our head to the left or to the right in this sort of a rolling action, if we held that tilt, what we'd find is that it's really this utricle macula that is most sensitive. And again, it has to do mainly with the fact that these hair cells are going to be activated because of the axis of depolarization and hyperpolarization would be activated as we tilt our head from one side to the next. Okay, so that's a bit about the organization of the hair cells and the otolith organs. We'll come back to this. What about the semicircular canals? Well, the semicircular canals are a bit more straightforward. There, the hair cells are found in these bulb-like structures that we find in here, and these bulb-like structures are called ampullae, or ampulla for a singular bulb. And within that ampulla, there's a sensory epithelium. We call that a crista, and that's where we find our hair cells. And in each crista, the hair cells are arranged basically just in one direction. So unlike our otolith organs where there's an axis of symmetry, there's no axis of symmetry in the semicircular canals. Within that ampulla, along that crista, all of these hair cells will either get deflected together in one direction towards the longest stereocilia or away from that longest stereocilium. Towards the longest is depolarization, away would be hyperpolarization. Now, I want to talk about each of these classes of organs and consider how the biomechanics of their function relate to the sensory transduction mechanism. And let's first start with our otolith organs. So here again is the macula of the otolith organ, and let's just say that this would be the macula of the utricle. And what we find is that these hair cells are not just projecting out into the endolymph, but rather there's a gelatinous membrane that sits right on top of the apical surface of this sensory epithelium. And yet on top of that gelatinous membrane are these calcium carbonate crystals that we call otoconia. And otoconia quite literally means ear stones. So we have basically a layer of calcium carbonate crystals. We can think of it really as a layer of pebbles that are sitting upon this relatively dense, relatively heavy gelatinous mass. So what would that mean if we were to tilt our head in one direction or another? Well, when we tilt our head, we're going to shift the distribution of that otolithic membrane relative to the fixed structures of the sensory epithelium. So if we have a static tilt, let's say in the backward direction, go ahead and tilt your head back if you like, what we find is that this gelatinous membrane, with the weight of it being pulled by the force of gravity, we find that that membrane would begin to slip in the downward direction relative to the fixed sensory epithelium. And the result is that the hair cells are going to be bent in the downward direction. Now remember the axis of symmetry that we found. So in this illustration, the hair cells that are here to the right are going to be T-polarized because they are being deflected towards their longest stereocilium. But the hair cells on the opposite side of the axis of symmetry are going to be hyperpolarized because they're going to be deflected away from their longest stereocilium. So within each macula of our otolith organs, half of the population of hair cells will be activated by a static tilt, whereas the other half will be deactivated or hyperpolarized. So this is not unlike the situation we talked about in the retina, where for the spot of light that strikes the retina, half of the population of ganglion cells for which that spot hits the receptive field will turn on. Those would be our on-center cells, and the other half will turn off. Those would be our off-center cells. So we can think of this symmetry in the macula of the otolith organ as being somewhat analogous to the on and the off structure of receptive fields in the retina. Only here now, rather than there being a physiological explanation, there's really a biomechanical explanation. The on and the off, or the hyperpolarization and depolarization, simply has to do with this axis of symmetry that runs through the membrane. Okay, well, let's consider now what happens when we accelerate our head in addition to when we tilt our head. So this would be our resting posture with the gelatinous membrane and the otoconia right on top of the otolithic organ. So our hair cells will be in a neutral position. And what I just described for you is the impact of that backward tilt. So now you're familiar with the idea that gravity would pull that otolithic membrane, and there would be a shearing force that would depolarize half of the hair cell population and hyperpolarize the other. Well, we can also activate this system if we accelerate our heads forward. So if we start walking, for example, or just lean forward with our head, basically what we're doing is that we are accelerating the sensory epithelium, and that will shear against the otolithic membrane because of the inertia that we would have as these membranes slip past each other as we accelerate the sensory epithelium, which is of course fixed to the bones of the head. So forward acceleration would be similar to this backward tilt, at least for this sensory epithelium. Now, movement in the opposite directions would be expected to produce the opposite physiological results. So a forward tilt of the head would result in gravity tugging forward that otolithic organ, and now that sensory epithelium should show the opposite physiological response. Now the hair cells that were depolarized by backward tilt will be hyperpolarized by forward tilt, and those that were hyperpolarized by backward tilt are now going to be depolarized. Likewise, when we decelerate, so if you're walking and you come to a stop, now what's happening is that this sensory epithelium is decelerating, creating a shearing force against the otolithic organ, as the forces of inertia eventually allow for the stabilization of this membrane back in line with the neutral position of the hair cell stereocilia. So deceleration is going to be similar to activating this membrane with a forward tilt. Now let's look at the physiological responses of the actual cells that are giving rise to the signals that can be recorded in the eighth cranial nerve. So if we were to tilt our head forward, what would happen is that there would be a significant elevation in the firing rate of axons in that eighth cranial nerve as long as we sustain the tilt. And the reason is simply that as we start that tilt and then maintain it, gravity has now pulled that otolithic membrane forward relative to the sensory epithelium. So these hair cells maintain their deflection of the stereocilia towards their longest stereocilium. That would be consistent with depolarization, so this would be a recording from an axon that innervates such hair cells on one side of that axis of symmetry. So these cells fire tonically, so we call this a tonic or sustained pattern of activation as long as the head is in its tilted position. And when we restore our head to neutral, then the firing rate returns to rest. Now, if we were to tilt in the opposite direction, the very same axon would be expected now to decrease its firing rate. And that's exactly what happens. So if we're recording from the cell that was activated by a forward head tilt with the backward head tilt, then that neuron is going to have a decrease in its firing rate. So it makes some sense then that there ought to be a fairly high level of spontaneous activity in this system, because otherwise it wouldn't be possible to decrease the firing rate if the firing rate were already nil. So having some significant measure of spontaneous activity allows this system to either be increased or decreased, depending upon the deflection of those stereocilia. Okay, so again, let me just emphasize the major physiological point that I want you to take away from this, and that is that when we move our head by linear acceleration or by tilt in the vertical plane, we are largely going to activate our saccule. And this is again because of the orientation of the sensory epithelium, which is largely in the vertical plane, but also the direction of organization of those hair cells. So static tilt forward and hold, and backward and hold, or a elevator type acceleration up and down, that's going to activate these hair cells that are otherwise in this direction. In the same way, the macula of the utricle is arranged to be sensitive to motions in the horizontal plane. So linear accelerations forward or to the side, as well as head tilt and hold to one side or the other, is going to activate the utricle macula more so than the sacculus. Now, like most complementary systems in neuroscience, there is some overlap, so we can expect that any one kind of head tilt or any one kind of linear acceleration is mainly going to activate one kind of membrane or the other, but the other one will contribute to the sensations that are derived from that movement to some degree. And certainly if we move along some oblique axis of acceleration or some oblique direction of tilt, we can expect both otolithic membranes to contribute to the sensations that are derived from that motion. Okay, so now let's focus in on the ampulla of a semicircular canal. So this is a bulbous expansion at the base of the semicircular canal. So this is where we find our sensory epithelium, which is called the crista. And overlying that crista is a gelatinous mass through which protrude the stereocilia of the hair cells. So this gelatinous mass here is called a cupula. And so we see the bundles of hair cells that are projecting into this cupula. Now again, there's no axis of symmetry that bisects the sensory epithelium as we saw in our otoliths. So there's simply one axis for depolarization that's present in a crista of a semicircular canal. Now this cupula creates a barrier to the flow of endolymph. And so what this means is that if we accelerate our head around an axis of rotation, it's something analogous to, let's say, rotating a cup of water. So the glass would be the membrane and the fixed components, and this cupula is indeed fixed here at its base along the crista, as well as on the more distal part of the ampulla. So if we were to turn that glass of water, the glass turns, right? But the water has some lag because of the force of inertia. The same thing is going to happen here in the semicircular canal. As we turn our head, the force of inertia is going to cause a deflection of this cupula. So let's have a look at that. So here's the semicircular canal at rest, and then if we were to rotate it, so we are actually accelerating our sensory epithelium with a turning of the head. The lag, or the inertial force, causes endolymph to essentially flow in the opposite direction. Really, it's the fixed structures that are moving. The endolymph is staying more or less in the same place. That causes displacement of this cupula. And as you can see, this displacement is going to deflect the hair cells in this crista towards the longest stereocilium. That's going to lead to depolarization of all of the hair cells together in this one crista. Now, we're turning our heads to activate this particular ampulla of a semicircular canal. It has a functional pair on the opposite side of the head. The turning of the head in one direction is going to activate the crista on the side of the turn, and it will deactivate or hyperpolarize the hair cells on the opposite side of the head in the corresponding member of the pair. So let's see what this looks like from a physiological perspective. So now we're recording the discharge rate of an axon that receives a synaptic input from a hair cell in the crista of a semicircular canal. And we see that as we accelerate, that is, as we begin to turn our head, we see that there is now a transient response where there's a temporary increase over the course of a couple of seconds in the firing rate of this eighth cranial nerve afferent. But as we attain constant velocity, so you can imagine if you start to turn around in circles, I'm not going to be able to do this very long because I'm going to get dizzy real quick. But in the first few seconds of rotation, my left horizontal canal began to increase its firing rate. But as I was maintaining that rotation, essentially the movement of the endolymph caught up with the movement of the fixed structures, and so the deflection of the cupula now relaxed back down to its neutral position. And so the velocity of rotation was maintained, but the deflection of the hair cells relaxed after several seconds of rotation. So that is why this response in the hair cells and in the eighth nerve axons that innervate the semicircular canals is phasic. Okay? It's only transitory. Now, as we decelerate, we essentially are producing the opposite biomechanical effect. That is, we are reducing the rate of rotation, and that's causing the endolymph to flow against the decelerating crista, or the decelerating cupula. And so that's going to now deflect the hair cells in the opposite direction. And that will produce hyperpolarization and a reduction in the release of transmitter on the eighth nerve afferent, and therefore a reduction in firing rate. And it will again take a few seconds to equilibrate the flow of endolymph and the flow of the fixed structures. So this is why the semicircular canals only operate with a phasic response rather than the sustained response that we saw in the otolithic membrane. I would encourage you to think through this again on your own. If you don't quite understand why would the otoliths give rise to a sustained response where the semicircular canals a phasic response, you might want to go back and think through this again to make sure that makes sense to you. It basically is explained by the biomechanics of sensory transduction. And lastly, I want to talk about the function of these pairs of organs on either side of the head. I alluded to this just a moment ago. But this is very important for understanding central processing in the vestibular system, and this is what we'll come to in the next tutorial. I want you to appreciate the fact that our otolith organs come in pairs. There are 2 utricles in either side of the head. There are 2 saccules in either side of the head. They tend to work together because they're arranged in the same plane. The semicircular canals, however, are a little bit more complicated because they're actually arranged orthogonally to one another within the same side of the head. So that means the functional pairs need to be thought of as those canals that operate in the same plane. Okay? So for the horizontal canals, it's pretty straightforward. Both horizontal canals operate in the same plane. But when it comes to the superior and the inferior canals, then we need to recognize that the superior canal in one side of the head is actually operating in the plane of the inferior canal in the opposite side of the head. And then vice versa. My right superior canal will be a functional pair with my left inferior canal. So this means that in order to activate these functional pairs, I would really need to rotate my head along the axis, or within this plane, orthogonal to the axis of rotation defined by this orientation. So this forward tilt to the right would activate my right superior canal and deactivate my left inferior canal. And tilt back would do the opposite. It would activate the left inferior canal, deactivate the right superior, and so forth. Okay? So if I rotated down and to the left, I'm activating my left superior canal. Rotate my head back and to the right, I'm activating my right inferior canal. Now you may be wondering just about the head nod kind of motion. Well, we're going to activate both superior canals to some degree, not as perfectly as if we turned directly in their axis of rotation, but a forward tilt is going to produce phasic activation in both superior canals, and a backward tilt is going to produce phasic activation in both inferior canals. Now, the simplest of all to understand would be simply the shaking of the head left and right along the z-axis of rotation. Okay? So what would happen there is that as we turn our head towards one side, let's just say the head turns to the right, we would activate the right horizontal canal. So here's the ampulla of the right horizontal canal. And because of the inertia effect, the endolymph is essentially forced against the crista along its axis of depolarization. So we have a nice increase in the firing rate of the 8th cranial nerve on the right side of the head. That very same rightward head turn causes the endolymph to actually move in the opposite direction that would be consistent with depolarization for the left semicircular canal. Consequently, if the left semicircular canal is firing away, when we make that head turn, now it's going to decrease its firing rate. And then after a few seconds, if we keep rotating around, then we would expect it to recover back to its neutral position. So the key principle that I want you to take away from this slide is that we activate the semicircular canal on the side of the turn. So if we turn to the left, we're activating the left semicircular canal, the horizontal canal. If we turn to the right, we're activating the right horizontal canal, and so forth. Forward turn activates the superior canals, backward turn activates the inferior canals. So what I really want you to understand is that when we get to the brainstem and talk about central processing, the brainstem is comparing the activity that's coming from both vestibular nerves. And if we turned our head to the left, we can imagine that in the horizontal canal system, leftward head turn would elevate activity in the left vestibular system and decrease activity in the right vestibular system. Whereas if we turned our head to the right, we'd have the opposite effect. Okay, so what the brainstem's really doing is comparing the afferent activity that's coming from these two 8th cranial nerves. Now imagine what would happen if you had a lesion or some kind of injury to the hair cells or to the eighth cranial nerve. You may find that the activity on the lesion side begins to drift downward. We call this unilateral vestibular hypofunction. If I had hypofunction on the right side, what's that going to make me feel like? Well, it's going to make me feel like I'm spinning to the left. And vice versa. If I had injury or damage to my left vestibular labyrinth or left eighth nerve, there will be hypofunction on the left, and it's going to make me feel like my head is spinning to the right. Well, that's a very unpleasant sensation, as you might imagine. Maybe some of you have experienced it for yourself. It illustrates the power of this vestibular system. And it's important that you understand these peripheral biomechanics and the means for sensory transduction. And this will allow us to now understand and discuss how the central processing stations operate and what are the consequences for the integration of these vestibular signals. So when I see you next time, we'll talk about central mechanisms of vestibular processing. Hello again. Welcome back to the second part of our set of tutorials on the vestibular system. In this tutorial, I'd like to speak to you about central processing. This tutorial will again emphasize the complexity of the human brain, and now as we get into the brainstem and to other stations of processing of vestibular information, we will be talking again about circuitry that is genetically determined, and it will form the foundation of the functions of the vestibular system and its impact on motor control systems. My learning objectives for you in this session are that I want you to be able to discuss the neuroanatomy and the function of one particular circuit that is very important in the operation of our vestibular system, and that's called the vestibulo-ocular reflex. And as we'll see, the vestibular system are very influential in stabilizing the movements of the eyes in our orbits. I want you to be able to characterize the contributions of the vestibulospinal projections in postural control. Another very important aspect of vestibular function is to stabilize our posture when the surface underneath our feet is moving. And lastly, I want you to be able to discuss the contributions of vestibular sensation to proprioception. So let me once again provide a brief overview of vestibular function. The vestibular labyrinth is an extension of the inner ear that's designed to sense the motions that arise from head movements and the inertial effects due to gravity. There are really two parts to this vestibular system. There are the otolith organs, and these sense static head position and linear accelerations of the head. Then there are the semicircular canals, and the canals sense rotational accelerations, and within both kinds of membranous organs, there are hair cells, and the deflection of the stereocilia of these hair cells is what accomplishes sensory transduction in these different divisions of the vestibular labyrinth. So in this tutorial, I really want to focus on what happens next. So the vestibular signals are relayed to integrative centers in the brainstem as well as in the cerebellum. And these signals are used to adjust postural reflexes and eye movements. These signals also reach parts of the parietal cortex where our normal sense of orientation in three-dimensional space is constructed. This is an important contributor to our body schema. That is, our understanding of the position of our body and its movements in the environment. Now, we also might have vestibular dysfunction from time to time, or perhaps as a result of injury or disease. And that vestibular dysfunction can lead to really a devastating sense of dizziness and disequilibrium. We call this vertigo. And these very powerful sensations arise when this circuitry is disturbed or when the sensory signals are dramatically shifted towards imbalance, even though the body itself may not be moving. And so these sensations are obviously integrated across multiple levels of processing, but ultimately at the level of the cerebral cortex, where these feelings of unease and dizziness are experienced in consciousness. Okay, well, let's now talk about central vestibular processing. So recall that the cells that grow their axons in the eighth cranial nerve are found in Scarpa's ganglia, and these ganglia provide for the communication of sensory signals from the hair cells and the otolith organs and the semicircular canals to the brainstem. So these Scarpa ganglion cells grow axons that proceed into the brainstem along the path of the eighth cranial nerve. And as they attach to the brainstem in the lateral part of the junctional region between the pons and the medulla, these axons innervate a set of cells that are part of a complex of nuclei that we call the vestibular nuclear complex. So these vestibular nuclei are found in the lateral tegmentum of the upper pons and the upper part of the medulla. Now there are some vestibular afferents that grow directly into the cerebellum, into a part of the cerebellum that we call the floccular nodular lobe, or sometimes we refer to this cerebellar division by its functional term, the vestibulocerebellum. So when we talk about the cerebellum, we'll spend just a little bit of time talking about this special division of the cerebellum that is devoted to processing signals that are relayed along the eighth nerve as well as through the vestibular nuclei concerning our sense of balance and equilibrium. Now, one of the major functions of our vestibular nuclei in the lateral tegmentum of the brainstem is to coordinate the movements of the eyes so that we can maintain stable fixation while our head and our body are in motion. Now, I want to talk just a bit about how this happens, and this occurs via a reflex, a sensory motor reflex, called the vestibulo-ocular reflex. So before I can talk about this reflex, I just want to make sure you're aware of the 6 pairs of extraocular muscles that move the eyes in the orbit. There's the lateral rectus muscle, which abducts or abducts the eye. There is the medial rectus muscle, which adducts or adducts the eye. The eye is elevated by the actions of the superior rectus as well as the inferior oblique muscle. The eye is depressed by the actions of the inferior rectus and the superior oblique muscle. And combinations of activation of these muscles allow for all the other possible motions of the eye within the orbit. So there are 6 pairs of muscles that attach to the sclera of each eye. And these 6 muscles are under the control of 3 cranial nerves. Those cranial nerves are the abducens nerve. The abducens nerve is cranial nerve 6, and it grows out from the abducens nucleus, which is a somatic motor nucleus in the caudal part of the pons. The 6th cranial nerve innervates the lateral rectus muscle. Now, moving up into the brainstem, near the junction of the pons and the midbrain, we have our next somatic motor nucleus for eye control, and that is the trochlear nucleus. So the trochlear nucleus is found along the dorsal midline of the tegmentum, but now in the upper portion of the pons. And this is a bit of an unusual nucleus because it grows its axon to exit the dorsal aspect of the brainstem, and then as it's exiting, it actually crosses the midline and innervates the contralateral superior oblique muscle. Now, this is pretty unusual. In fact, it's a very unusual motor nerve in 2 respects. It's the only motor nerve that exits the dorsal side of the central nervous system, and it's the only motor nerve that supplies innervation to contralateral muscle. Okay, so the abducens nerve, nerve 6, does the lateral rectus, the trochlear nerve, nerve 4, does the superior oblique muscle. The rest of these extraocular muscles are innervated by axons that grow out from the ocular motor nucleus in the midbrain and send their axons through the third cranial nerve. So here's our ocular motor nucleus up in the midbrain. Again, a somatic motor nucleus, so it's found along the dorsal midline of the tegmentum, but now up into the midbrain. And these axons grow out and supply the remaining muscles, the superior and inferior rectus muscles, the medial rectus muscle, and the inferior oblique. So now we're ready to talk about the circuitry in the brainstem that mediates the vestibulo-ocular reflex. Now, before we get into the details here, I want you to understand the purpose and importance of this reflex. Imagine that you need to fixate on some near object, and I would encourage you to do so. I'm going to fixate on the tip of this pen, and now turn your head from side to side while you fixate on that pen. So hopefully you can see what's happening in my own orbits as I turn my head from side to side. When I move my head to the right, my eyes shift toward the left. When I move my head to the left, my eyes shift towards the right. It's truly one of the remarkable sensory motor reflexes we have in our bodies. The movements of our eyes are exactly matched to the movements of our heads, both in amplitude and in velocity. If that were not so, we would not be able to maintain fixation during the movements of our head. So how is this possible? Well, this figure 14.10 illustrates the circuitry that make this possible. If we were to turn our head, let's say, towards the left, we would need to turn our eyes back towards the right. So if to rotate my head to the left, hopefully you can see that my eyes are turning to the right. So turning my head to the left would be consistent with activating my left semicircular canal. And so what we would want to see happen is a turning of the eyes towards the right. So what is it going to take to turn my eyes to the right? It's going to require the activation of my right lateral rectus and my left medial rectus. These muscles will contract and they'll tug my eyes over to the right. Well, in order to allow my eyes to smoothly rotate to the right, it would be very helpful if we reduced the muscle tone in the antagonistic muscles. So that means as I'm contracting my right lateral rectus, it makes sense to reduce the tone of the right medial rectus so the eye can smoothly shift to the right. Likewise for my left eye, while my right medial rectus is contracting, it makes great sense to want to relax the left lateral rectus muscle. And this will allow the globe to smoothly turn towards the right. So this should give you some sense of how this happens. If the signal is leftward turning, activating my left semicircular canals, that's the input signal. The output is turning my eyes to the right. I'm going to need to have some signal that crosses the midline and activates my right abducens nerve. I need a signal that will activate my left ocular motor nerve. And then I need to have some kind of signal that will suppress the antagonistic muscles. So let's see how this works. Again, with activation of, let's say, ganglion neurons on the left side that innervate the horizontal canal there, we would engage a series of neurons that sit in this vestibular nuclear complex. One of these neurons is going to release an excitatory neurotransmitter in the abducens nucleus of the opposite side of the brainstem. That abducens nucleus then is going to innervate the lateral rectus muscle and cause it to contract, tugging that opposite eye, in this case the right eye, towards the lateral side of the visual field. Okay, so this is going to achieve that rightward eye movement. Now what about what's going on with the left eye? Well, we need to activate the medial rectus muscle of the left eye. And in order to do that, we need to have a second kind of neuron that grows from the abducens nucleus to the ocular motor nucleus. This is called an internuclear interneuron, or an internuclear neuron. So it's going to release an excitatory transmitter, and drive the activation of the oculomotor alpha motor neuron that will cause contraction of this medial rectus muscle and the turning of the left eye towards the right. Okay, now what is it going to take to relax the antagonistic muscles? The way that this happens is via an inhibitory interneuron. And that inhibitory neuron grows out of the vestibular nuclear complex and suppresses the firing of the alpha motor neuron of the abducens nucleus on the same side of the brainstem, and it suppresses that internuclear neuron that connects the abducens nucleus with the oculomotor nucleus. So essentially we activate one pair of cells and deactivate the corresponding pair on the other side of the brainstem through synaptic inhibition. And this allows us to achieve the functional goal of turning our eyes directly opposite the rotation of the head. Now, there's a phenomenon that you need to know about. It can be an important clinical sign, and it's called vestibular nystagmus. Now, nystagmus is one of those interesting words that it's worth knowing its meaning. It means a nodding of the head. So, nystagmus is something that we see in the eyes, but the action is very much like nodding of the head as if you're falling asleep. So what do we tend to do sometimes when we're listening to a boring Coursera lecture is that we might doze off, our head goes through a slow phase, and then we might snap back up as we sort of wake ourselves up by the action of nodding our head forward. So the idea is that there's a slow phase, and then there's a rapid phase. Slow phase, and then a rapid phase. That's nystagmus. So it's a rhythmical form of reflexive eye movement that includes the slow component in one direction that is interrupted by a very fast saccade-like component in the opposite direction. So if my hands represent movements of the eyes, you can imagine the eyes moving slowly to one side and then quickly snapping back and moving slowly and snapping back. Now, vestibular nystagmus is normally driven by persistent head rotation. So if you were to spin someone around in a chair, you might want to try this with a willing volunteer, and then suddenly stop that person. What you might see is that their eyes are going to be in nystagmus. That's because for a few seconds now, the endolymph is going to be deflecting the cupulas of the horizontal canals. And you should see a very predictable type of nystagmus with the eyes going in the direction opposite the movement of the head, and then they'll snap back and continue to move opposite the direction of rotation until that endolymph stabilizes relative to the fixed structures of the horizontal canal. Now, it's important to recognize that it's the slow component of nystagmus that's driven by the vestibulo-ocular reflex. The fast saccadic component, that reset, that is a different kind of reflex that repositions the eyes in the orbits. That's not a function of the VOR, the vestibulo-ocular reflex. That has to do with more of a sensory motor integration reflecting proprioceptors from eye muscles driving a quick reflexive reset of eye position in the orbit. So what's important is to realize that the vestibular nuclear complex drives the slow component of vestibular nystagmus. Now, we can learn a lot from watching the movements of the eyes, especially if nystagmus is present. The type of nystagmus we see, that is the direction of the slow component of the eye movement, is an indication of the balance of activity that we find arriving from the two eighth cranial nerves. And that balance is critical, because if the balance is offset, either because we are actually rotating our head or because there's hypofunction on one side of the vestibular system, then there will be a drive of the eyes consistent with the vestibulo-ocular reflex. Okay, so if we turn our head to the right, we're elevating activity in the right side. decreasing it on the left, that's going to drive our eyes to the opposite side. But also, if we were to have hypofunction on the left, such that there is now an imbalance, the eyes would be driven in the slow phase of nystagmus towards the left, as if we were actually turning our head to the right, but we're not. So if this were the situation with hypofunction on the left side, we would expect the slow phase of nystagmus to go to the opposite side of the head, away from the elevated side, so to the left, towards the side of the hypofunction. And then the quick phase would reset. So hypofunction to the left means that the slow phase is towards the left, and then the quick flick back to the right. So when you're evaluating clinical patients for the presence of nystagmus, it's important to keep in mind that you're looking for evidence of this pathological alteration in the balance of activity between the two sides of the vestibular nuclear complex. And this is what gives rise to the expression of nystagmus under conditions that wouldn't normally induce this kind of oculomotor behavior. So obviously you want to have your patient's head stable and in neutral position while you're examining this patient and the possibility of nystagmus. Now, you may induce certain head movements as a variable which will test the operation of the vestibular system, but I'll leave that discussion for the clinicians who may be teaching you about how to do a thorough vestibular examination. Here in medical neuroscience, what's critical is that you appreciate the effect of an imbalance of activity on the two sides of the vestibular system, and what that would do for the induction of nystagmus in the movements of the eyes. Now, we've been emphasizing movements around the z-axis that would be consistent with shaking the head to the left or to the right, and that obviously is focusing on the activities of the horizontal canals. But one can have nystagmus really in any direction. One can have a rotation of the eyes that would be consistent with stabilizing gaze against movements of the head in the nodding direction, okay? So that would imply that if there were dysfunction associated with a superior canal or an inferior canal, there may be nystagmus where the eyes would perhaps drift up and flick down, or maybe drift down and flick up, or there may be some rotational component to the nystagmus that would reflect the integrated activity of some combination of canals on one side of the head versus the other. But the key principle is that the imbalance in the signals arriving from the two vestibular nerves are what will drive the vestibulo-ocular reflex. Okay, now let's turn to the second major sensory motor reflex that's driven by the vestibular system, and it concerns adjustments of posture. So this is another major function of these nuclei that are found in this vestibular nuclear complex. They produce reflexive adjustments of posture that compensate for movements of the head. So in order to do so, there are descending projections from these vestibular nuclei in the lateral tegmentum of the upper medulla and the caudal pons down into the spinal cord. And they contribute to what we will describe as a medial system of descending axons that regulate posture. So I emphasize medial because we will find these axons in the most medial parts of the white matter of the spinal cord. Now, this will differentiate these systems from the axons that we find in the lateral columns of the spinal cord that are associated with the cortical spinal pathway that are mainly governing what we do with our distal extremities. So the medial spinal cord pathways are concerned with posture. The lateral spinal cord pathways are concerned with what we do with our hands and with our feet, what we might call skilled behavior. Now, this medial and lateral dichotomous arrangement of systems in the spinal cord is going to be much more clear when we get into the motor systems, but there's some peril in introducing that here, because when we identify the connections from the vestibular nuclear complex to the spinal cord, we realize that there are really two tracks that we want to be concerned with. One is called the medial vestibulospinal tract, And these axons run down through the medial part of the white matter of the spinal cord. And the other is called the lateral vestibulospinal tract. Now, it's called lateral because these axons are in a more lateral position in the white matter of the spinal cord, but they're still part of the medial descending system. So I want you to recognize when we get into our unit on motor control that both the medial and the lateral vestibulospinal tract are concerned with postural control, and they will innervate the medial part of the ventral horn of the spinal cord. So we'll come back to that point, but for now, I just want you to know these terms: medial vestibulospinal tract and lateral vestibulospinal tract. So the medial vestibulospinal tract arises from the medial vestibular nucleus, and it gives rise to bilateral projections that innervate mainly motor neurons in the cervical cord that are concerned with the movements of our head and our neck, and perhaps as far down as the segments of the cervical cord that are concerned with the extension of the arms and the actions of more of our proximal upper extremity muscles. So here's where this is important. Imagine that you happen to trip and you're falling forward. What would make great sense would be that you protect yourself against the impact by extending your arms and that you get your face out of the way. So there is a reflex that is triggered by the forward acceleration of the head. So activation of the superior canals will lead to the dorsal flexion of the neck and the extension of the arms. This is a vestibulocervical reflex connecting the vestibular system to the cervical spinal cord, and it's bilateral. Okay, so that makes good sense. We want bilateral extension of the arms, and we want to be able to pull the head back symmetrically on both sides of the neck. Now, the lateral vestibulospinal tract is a bit different. The lateral vestibulospinal tract originates in the lateral vestibular nucleus and the spinal vestibular nucleus, and it gives rise to descending projections that run, again, through more or less the anterior medial white matter of the spinal cord, but they do so on the ipsilateral side of the spinal cord, and they innervate motor neurons that are primarily now in the lumbosacral enlargement, because what this tract is mostly concerned with is maintaining the extensor tone of the anti-gravity muscles of the lower extremity. So here's this system in action. Imagine that you're riding on a moving bus or a train and it's crowded and you can't find a seat. So you're standing up on that train or that bus while the floor is moving underneath your feet. And so there are lots of jolts and bumps along the way, lots of unexpected rotational accelerations of your head as you're being jostled around with the movement of the train or the vehicle. And in order to maintain that upright posture, we need to increase the tone of our extensor muscles in the legs. And we do so in an ipsilateral fashion. That is, if I begin to fall to my right, I'm going to activate my right-sided vestibular labyrinth, and that needs to send signals down the right side of my spinal cord and activate the motor neurons that will extend the muscles of my right leg so I can support myself and not fall over to the right. If I were to fall forward while standing up on that train, then activation of the superior canals ought to allow me to brake myself against possibly falling forward by extending my anti-gravity muscles in the forward direction, and so on for each kind of movement. So it makes sense that this needs to be an ipsilateral pathway so that we can support ourselves against motion to one side or the other. So again, it's important to recognize that the medial vestibulospinal tract is mainly a connection to the cervical spinal cord, while the lateral vestibulospinal tract really runs the length of the cord, but it's especially concerned with the activation of extensor muscles in the lower extremities. And lastly, I'd like to just talk very briefly about higher vestibular processing. So obviously our vestibular system gives us a sense of motion, a sense of position of our head relative to the environment, and that environment is defined in large measure by our visual and our auditory signals that are integrated with other dimensions of mechanosensation that are derived from our somatic sensory system. And all of these signals come together in the parietal cortex. So how do vestibular signals get to the parietal cortex? Well, there are projections from some of the nuclei of the vestibular nuclear complex that project into the thalamus, somewhere into this ventral posterior complex of the thalamus, very near where our dorsal column, medial lemniscal, and anterolateral system afferents terminate. And then cells in this ventral posterior complex of the thalamus give rise to projections into the parietal lobe. There seem to be some projections that end near the face representation in the somatic sensory cortex. And these projections seem to be targeting Brodmann's area 3A, which is where we have representation of our proprioceptive signals. And there is a more posterior target in Brodmann's area 5 that seems to receive this input from the thalamus concerning vestibular signals. Now, this information is integrated in the parietal lobe together with this visual and auditory and somatic sensory information that helps to define our image of our body relative to the environment and our motions through that environment. And finally, there are some additional vestibular connections I'd like to mention. The vestibular nuclei also receive input from other sensory modalities, including somatic sensation, audition, probably very indirectly through visual pathways that run through the midbrain and the pretectum. And these stimuli are together integrated with our vestibular senses and help orient our head relative to the stimuli we encounter in the motions that we generate. As I mentioned briefly, the vestibular nuclei are intimately connected with a portion of the cerebellum that we call the floccular nodular lobe, or the vestibulocerebellum. And the vestibular nuclei have something of a privileged relationship with the cortex of the cerebellum in this one division. And there's a sense, as we'll discover, that the vestibular nuclei can be considered a set of deep cerebellar nuclei that are found in the brainstem rather than on the roof of the fourth ventricle. So we'll come back and see that when we study the cerebellum. Now, finally, the vestibular nuclei are connected to parts of the reticular formation that are found in the core of the brainstem that are integrating visceral sensory signals and giving rise to visceral motor commands as well. So you may wonder, well, why should you feel ill when you have these unusual vestibular sensations that are consistent with motion, even when there's no motion happening? Or maybe you're wondering, well, what about seasickness? When there's this vestibular modulation that's going on that ultimately might lead you to feel quite ill, and you might actually engage in visceral motor activity, such as vomiting. Well, there are vestibular connections to the reticular formation that will engage these coordinations of visceral motor activities that might actually produce that motor action. And then there are ascending connections from the reticular formation that will influence our feelings of wellness. And it's through those integrated signals together with the more direct impact via the connections from the thalamus to the parietal cortex that result in these feelings of illness and dizziness and ill-being. And if any of you have ever been motion sick or seasick, or if you've ever had a condition called benign paroxysmal positional vertigo, you know the power of the vestibular system to generate feelings of illness even in the absence of motion. Well, I hope this has been helpful to you. We won't attempt to identify the precise location of the pathways for vestibular processing, but I do want you to know where the vestibular nuclei are. So if you haven't yet done so, why don't you jump into either the atlas pages at the back of the textbook or into Sylvius and find these vestibular nuclei. So I'll do that for you in just a moment. So perhaps you might want to grab the textbook or open Sylvius and you can follow along. Okay, here we are in our brainstem atlas within Sylvius. So I just want to navigate over to the vestibular nuclei. So we're going to find them in the caudal part of the pons, in the upper part of the medulla, and we'll find them in the dorsal and lateral aspect of the tegmentum of the brainstem. Okay, so we're about the level of the mid-pons here. If we go down just a few millimeters, and look in this dorsal lateral tegmentum, now we see some nuclei that are part of our vestibular nuclear complex. Okay, we are just above the junction of the pons and the medulla here, so we would expect to be near the upper part of this complex. If we go down closer to that junction, now this looks more like the upper medulla, which indeed it is. We see a medial vestibular nucleus, a spinal vestibular nucleus. Don't be concerned about the names of the individual nuclei, but I just want you to understand where these nuclei are found in the tegmentum of the upper medulla and the caudal pons. Here's a little bit of the nerve root of the 8th nerve here, and our cochlear nuclei would be out here, just on the lateral aspect of our inferior cerebellar peduncle. So just on the medial side of that peduncle is where we find our vestibular nuclei. So I want you to appreciate sort of the regional location of where we find these nuclei. Dorsal and lateral tegmentum of the upper medulla and the caudal pons, right next to the inferior cerebellar peduncle, and just dorsal to our spinal trigeminal tract and nucleus. Okay? Now this is important because we may discover in our clinical studies a patient that has had a stroke that affects this dorsal lateral region of the upper part of the medulla. This can happen with an infarction of our posterior inferior cerebellar artery, for example. If that should be the case, we would expect there to be this collection of neurological signs and symptoms that we can relate to this region of the brainstem. We would expect to see a problem with our trigeminal system, our spinal cerebellar systems, and now we would expect to include problems with our vestibular system. So if we had damage to, let's call this the left side, the left vestibular nuclear complex, we might expect there to be vestibular nystagmus that would be consistent with turning of the head to the right. That nystagmus would be a slow phase of movement to the left and then a quick beat back to the right. So if we saw that vestibular nystagmus together with a lack of sensitivity to painful stimuli on the left side of the face, and perhaps some incoordination of the left side of the body, then we might conclude that indeed we've got this kind of a lesion of the left dorsal lateral tegmentum of the upper medulla. So this is why regional anatomy is critical for interpreting clinical case studies. And the way we get there is building our knowledge one system at a time. And so for today's lesson, I want you to appreciate the fact that these vestibular nuclei are located right here, the dorsal lateral tegmentum of the upper medulla caudal pons. So I hope you enjoyed this brief tour of the vestibular system, both peripheral mechanisms and now central processing. And I hope you have time to put your vestibular system in action. I know I need to. I'm due on my basketball court in my driveway to have a little basketball game with my son, and that is sure to activate all of my vestibular apparatus, I'm sure. So let me go do that, and I'll see you next time. Welcome to this tutorial on the chemical senses. The chemical senses pertain to a set of special sensory systems associated with the head region of the body, and we are going to discuss them in several parts. In this part, I'd like to give you an overview of the chemical senses. And this discussion about chemical sensation is going to, again, illustrate for you the complexity of the brain as the body's most complex organ. And as we get into our special sensory systems for the chemical senses, we'll see once again evidence of genetically determined circuits that provide the foundation for the functions of the nervous system. And when it comes to discussion of these chemical sensory systems, I think we'll see some really remarkable examples of where there is genetic expression in space and time that influences the structure of circuitry that provides for, in this case, the foundation for chemical sensation. So I have just a brief tutorial for you. In this particular part, it will provide an overview of the chemical senses. And my goal for you is that you'd be able to summarize the organization of the neural systems for the chemical senses. So let's get started. And just a simple comment that will set the stage for our more detailed studies of olfaction and gustation in just a bit. Our chemical senses are special sensory systems primarily in the face, but also in the cavities within the head. And these are systems that detect minute quantities of chemical molecules in the environment. And these chemicals can serve a variety of purposes, and that's what I want to help you understand in this brief overview. So consider, for example, first airborne molecules. So the air is full of odorants, full of molecules that have a particular shape and structure to them, particular chemical qualities, and there are specializations of receptors in the face and in the head that interact with these airborne molecules. Specifically, these airborne molecules interact with receptors that produce a sense of smell, and this is what we call olfaction. So olfactory sensations are a response to the presence of these airborne molecules. Now, some of these molecules can actually produce irritation to tissues in the body. They are potentially damaging, and it makes great sense that we would have a chemical sensory system that would be dedicated to detect these potentially irritant molecules. And that's where the third major chemical sensory system comes in. It's called the trigeminal chemosensory system. Now, in addition to airborne molecules, of course, there are molecules that are mostly water soluble and also lipid soluble that we ingest. So we put these molecules into our bodies, obviously through our mouth, and these molecules have an opportunity then to interact with the mucosa that is present in our oral pharynx. So as we interact with these ingested molecules, these molecules can then activate a variety of receptors that give rise to our sensation of taste. This is what we call gustation. So ingested molecules give rise to gustatory sensations. Now, you may be wondering about flavor, which, as we'll talk about as we move along here, is actually a combination of really all three of these chemosensory pathways when we think about it. Consider, for example, eating your favorite spicy food. There is a particular smell that might first arouse our appetite when this plate of food is presented to us. And then, of course, as we begin to eat it, there is the consumption of these molecules that we begin to ingest and they begin to interact with our gustatory receptors. But if it's spicy, there may also be a mild irritant quality to it that can drive sensations through our trigeminal chemosensory system. And somewhere in the brain, and I'll tell you where we think it actually happens in just a little while, these various sensory systems are combined. And they are combined in a sense that gives us our quality that we call flavor. Well, in addition to feeding behaviors, these chemical sensory systems provide really a number of important functions, beginning with nutrition. So these chemical sensory systems allow us to assess the palatability or the desirability of those foods and drinks that we consume. And this is quite important, as I think we all can appreciate, perhaps not so much in our modern societies, but certainly as we sample the foods of the world, wherever we may be, We are always on guard, are we not, for the palatability of food, trying to avoid potentially harmful substances. There are a variety of physiological functions that are regulated by our chemosensory systems. These include memory, visceral motor behavior, reproductive cycles, and very importantly, infant paternal behaviors and infant maternal behaviors. There are a variety of social interactions that are mediated via the chemical senses. Through the chemical senses, we evaluate self and we evaluate others. As I mentioned already, safety becomes an important domain of chemical sensation, not just for the ingestion of potentially harmful substances, but also our interaction with volatile chemicals in the environment that might be mildly irritating at low concentrations and potentially quite harmful at higher concentrations. And then lastly, it's through the chemical senses that so much of our hedonic reward system is tuned. And what I mean by this is those chemical messages that either we ingest or that we sniff or that we otherwise interact with our chemosensory systems that can drive a sense of pleasure. And one can imagine lots of examples of this: an attractive perfume, the scent of your favorite flower, pleasurable foods and drinks, and quite interestingly, also the possibility of there being pheromones. Now, as I'll describe as we get a little deeper into olfaction, we know that the old world primates, including humans, lack the specializations in the olfactory epithelium and in the peripheral parts of the olfactory system to be sensitive to pheromones in the way that non-old world primates and other non-primate mammals may be. But nevertheless, there is some tantalizing bit of evidence to suggest that our behaviors are in fact influenced by chemical messages in a way that would be consistent with pheromone interaction. So that would be an interesting discussion to bang around, perhaps on the discussion forum or elsewhere. Well, I hope you've enjoyed this brief overview of where we're going to go over the next couple of pieces to this tutorial on the chemical senses. And I look forward picking up with you in just a moment in a discussion of the olfactory system. So I'll see you then. Okay, I think we're ready now to explore the chemical senses, beginning with the sense of olfaction. As I've already told you, this aspect of our consideration of the chemical senses will reveal again the complexity of the human brain and will provide us an opportunity to explore some really fabulous circuitry that connects the sensory periphery in the olfactory system to the brain. And I think you'll be surprised with some aspects of the specificity of that relationship that reflects genetic instructions that are played out both in brain space and in time as the nervous system develops. And all of this is critical for the foundation of the olfactory sense. So my learning objectives for you in this session, in this part of our tutorial, are really threefold. I'd like for you to be able to characterize the peripheral and central organization of the olfactory system. I'd like for you to again focus on this critical issue of sensory transduction that's been central to all of our considerations of sensation so far in the course. And I'd like for you to get a feel for how information is actually encoded in the olfactory system. I think one of the values in studying the chemical senses is that we discover perhaps some surprising means for coding information in a sensory system that, especially in olfaction, seem to be quite different than the kinds of coding mechanisms that we've seen so far in somatic sensation, in vision, and even in audition. All right, well, let's begin with an anatomical overview of the olfactory system. So, as I've already mentioned to you, olfaction begins with airborne molecules interacting with receptors. And those receptors are found in our olfactory epithelium. And our olfactory epithelium is found in the dorsal and medial aspect of our nasal passageway, and it's there that we find our receptor cells. We'll have a closer look at those receptor cells in just a little bit, but for now I just want to place them for you. So our olfactory epithelium then is where sensory transduction occurs. So our sensory cells then are found within our olfactory epithelium, which is shown at a little bit higher magnification here to the right. And these cells grow an axon that passes through perforations in the ethmoid bone, and we call this region of the ethmoid bone the cribriform plate. And these axons enter a part of the brain called the olfactory bulb. And there they make synaptic connections with neurons that are in the bulb and are actually part of the brain. Now, if you remember what the ventral surface of the brain looks like from our tutorials where I showed you the actual human brain specimen, you might assume that the olfactory bulb and this long connection is actually a cranial nerve. Well, it's not. The olfactory bulb is part of the brain. The cranial nerve that we associate with olfaction represents these axons that pass through the cribriform plate. So this is our first cranial nerve 1. It's the axons of the primary sensory neurons that have a cell body in the olfactory epithelium and grow an axon through the cribriform plate to make synaptic connection in the olfactory bulb. This long extension then that connects the olfactory bulb backward toward the brain, this is called the lateral olfactory tract. So again, not a nerve, but an extension of the brain. The cells in the olfactory bulb that grow the axons that form this lateral olfactory tract, they are called mitral cells. We'll talk more about that in a little while, but for now I'll just mention that the mitral cells are then the principal projection cells that connect the olfactory bulb to the rest of the brain, and as we'll see, these structures in the brain are part of what we call the olfactory cortex. Okay, so here more schematically, we have our olfactory epithelium here, which is where we find our olfactory receptors. The first cranial nerve connects those receptor neurons to mitral cells in the olfactory bulb. And there are other cells as well that we'll talk about when we look in more detail at the cellular structure of the olfactory bulb. So the axons of the mitral cells project through the lateral olfactory tract to a series of targets that are found in the ventral and medial aspects of the forebrain. Now collectively we call these targets the olfactory cortex. Some of these structures are quite prominent and clearly are cortical in nature, such as the piriform cortex. Here we're spelling it with a Y. You'll notice in my handout I spell it with an I, P-I-R-I. You'll see spellings both ways, so either spelling is acceptable. Don't worry about that. Another major cortical structure that is clearly laminated and recognizable as cortex is the entorhinal cortex. So this is cortex a little bit more posterior back on the medial aspect of the temporal lobe. It's part of what we call the hippocampal formation. Now, these two other components, the olfactory tubercle and the amygdala, these are structures that we consider to be corticoid structures. And so this is simply a way of saying, well, they are derived from the same kind of embryological tissue that form the beautiful laminated cortex. However, the organization of the cells is not quite so clearly laminar. So from that perspective, we call this corticoid. Now, I should emphasize that each of these divisions of the olfactory cortex are heavily interconnected with one another. While sometimes we tend to focus on the piriform cortex, really it's this entire extended network of cells that constitute our olfactory cortex. Well, in addition to intrinsic associational connections, these divisions of the olfactory cortex also have projections to other parts of the brain. And this includes the thalamus, the hypothalamus, and especially important is the orbital and frontal parts of the prefrontal cortex. That is the part of the frontal lobe that sits just above the orbits of the eyes. as we'll come to discuss as we move along through this set of tutorials, it's here in the orbital frontal cortex that information from all of our chemosensory systems is combined with somatic sensation and even visual sensations. And it's in this part of the brain that our concept of flavor appears to be represented, as well as a sense of the rewarding value of food. Now, of course, in addition, food can be a powerful trigger for memory and for recall, so it makes sense that the entorhinal cortex has direct access to the circuitry of the hippocampal formation, where new declarative memories are formed. Now let's look at these brain regions from an anatomical perspective, and I'll go ahead and show you my brain model just to remind you in a bit more realistic fashion what we're actually looking at here. So I think you can recognize nicely the olfactory bulb and the lateral olfactory tract that connects the olfactory bulb back to the olfactory cortex. And even in this brain model, as you may remember from looking at the actual human brain, it does look like a nerve, but again I would emphasize that the olfactory bulb is really part of the human brain. Well, the lateral olfactory tract then connects back to the inferior and posterior part of the frontal lobe, right near the junction of the frontal lobe and the temporal lobe. That's where we find the beginnings of our olfactory cortex. Well, now, to look at our figure from our textbook, that cortex is illustrated here in the green shade, and the first division that we encounter of that cortex is the olfactory tubercle. So this is really a ventral part of the striatum, so it sits just below the main bulk of the basal ganglia. We'll get to talk about that in the next unit, but just to help you localize this region, it's just dorsal and a bit anterior to the level of the optic chiasm, which we see right here on the ventral aspect of the brain. Well, the rest of the olfactory cortex flows into the medial part of the temporal lobe. So there's a junctional region where the temporal lobe attaches to the inferior and posterior part of the frontal lobe. It's there that we find this division that we call the piriform cortex. So this illustration perhaps is just a bit too generous, indicating a more medial and perhaps a more ventral position of the piriform cortex. But most of the piriform cortex is actually tucked underneath this little region where the temporal lobe joins the frontal lobe. Well, that leaves us with the rest of this medial parahippocampal gyrus, and that's where we find the cortical divisions of the amygdala and the entorhinal cortex, which receive the inputs from the mitral cells of the olfactory bulb. Well, now that you have a bit more information about where the olfactory cortex is present, I want to make just a couple of general points about the organization of these olfactory structures that are worth noting as we discover this anatomy. First of all, I want you to notice that there is no thalamic relay between the sensory structures that we might consider to be more peripheral, such as the olfactory bulb, and the cortex. Now, in all of the other sensory systems that we've evaluated so far, you'll recall that there is a nucleus of the thalamus that receives ascending or incoming sensory information and projects that information into cortex. And this, we think, is quite important for how these sensory systems operate. The thalamus is something of a gatekeeper to the flow of incoming sensory signals to the cerebral cortex. Well, this doesn't seem to be the case in the olfactory system. There is a connection to the thalamus, but it happens after information has been processed in the cerebral cortex. So there's no obligatory thalamic relay between the olfactory bulb and the olfactory cortex. So the second point worth highlighting is that as we detail the organization of the cortex itself and consider the topic of sensory coding, what will be very clear is that there is no known map of the sensory environment. And there may not even be a clear map of the sensory periphery at the level of cortical processing. Now, there are very precise rules that help us understand how our sensory cells are related to specific neurons in the olfactory bulb. The challenge in understanding olfaction is that those rules are not conserved as the olfactory bulb projects back into the olfactory cortex. So at least no one has yet demonstrated in any compelling fashion that there is something like a topographic map of the sensory environment in the olfactory cortex in the way that we've seen it for a body map in the postcentral gyrus, a map of the retina or the visual environment in the occipital cortex for vision, or even a map of tonotopy or a map of the basilar membrane in the auditory environment. So it's as if the rules of coding seem to be different in the olfactory system, and that makes it very much worth exploring and understanding. Now let's turn our attention to the topic of sensory transduction in the olfactory epithelium. So here we have a closer look at the olfactory epithelium, and what we discover are the presence of several types of cells that are present in this epithelium. These spindle-shaped cells, these are the mature olfactory receptor neurons. These are the ones that are going to do the job of sensory transduction. These cells sit within an epithelium that is comprised of supporting cells and basal cells, and some of these basal cells will go on to differentiate and divide, and what we discover is that among this basal cell population is a set of neural stem cells, which from time to time will divide and produce new mature olfactory receptor neurons as olfactory receptor neurons are lost to degeneration or to injury and disease. In addition to the supporting cells, there are glandular cells that produce a thick mucus that covers the upper portion of this olfactory epithelium. So the way odorant molecules interact with our sensory cells is by passing into the nasal passageway and diffusing through this mucus to interact with these olfactory cilia. So these are hair-like extensions from this terminal bulb at the end of the dendrite of this olfactory receptor neuron. And embedded in the membrane of this olfactory cilia then are the olfactory receptor proteins that interact with the odorants. The odorants then will bind to specific molecular receptors that are expressed on the membranes of the cilia, and through a sequence of molecular reactions, the binding of an odorant to a receptor leads to the depolarization of the olfactory receptor neuron and the generation of an action potential at the axon hillock region, where the axon emerges from the cell body. And with the generation of an action potential in the axon hillock, that signal can then propagate along the axons of the first cranial nerve through the cribriform plate and into the olfactory bulb. So now let's consider these molecular mechanisms that generate the depolarization in these olfactory receptor cells. And now let's turn our attention to the mechanisms of sensory transduction in the membrane of that cilia that is present at the apical end of the dendrite of the olfactory receptor neuron. So what we find here is a molecule that we've actually encountered a few times before. The odorant receptor molecule is a G protein coupled receptor. That is, it's a receptor that interacts with an odorant molecule, and on the cytoplasmic surface of that receptor bind a set of G proteins. The molecular structure of this receptor makes it part of the 7 transmembrane class of G protein coupled receptors, the same class that we first encountered when we studied metabotropic receptors for neurotransmitters. We encountered this class of proteins again when we looked at the mechanisms of phototransduction in photoreceptors. The opsin protein that interacts with the retinal molecule is an example of one of the 7 transmembrane G protein coupled receptors. So I think it is so fascinating that this same molecular structure has shown up in so many different places in the nervous system. And in each of these places, the mechanisms involve transducing some kind of an event, be it the binding of a neurotransmitter, the binding of an odorant, or a conformational change in an organic molecule when a photon strikes it, to a second messenger system that is activated through a set of G proteins. And in the olfactory receptor neuron, this transduction cascade involves a G protein that we call G-olf, or that subscript identifies this as a particular G protein that's involved in transducing olfactory signals in olfactory sensory neurons. So the odorant interacts with its receptor, the G proteins are activated, and the activation of these G protein then interacts with a downstream target. And the principal downstream target is adenylyl cyclase 3. And when this enzyme is activated, then second messenger in the form of cyclic AMP is produced. So cyclic AMP levels rise when the odorant interacts with the olfactory receptor. The production of cyclic AMP in turn gates the opening of a cation selective channel. This allows for calcium and sodium to enter the cytoplasm of the olfactory receptor neuron. This leads to the depolarization of this neuron. Now there's even more synergy that happens within this olfactory receptor neuron related to these second messenger systems. As calcium begins to rise, then calcium interacts with calmodulin, and this interaction of calcium and calmodulin then gates a chloride channel, and that channel opens, allowing chloride ions to diffuse from inside to outside of the cell. And as that negative charge leaves the inside of the cell, this amplifies the depolarization of the olfactory receptor neuron. So together, the influx of sodium and calcium ions and the efflux of chloride leads to the production of the generator receptor that ultimately can lead to the activation of our voltage-gated sodium and potassium channels at the base of this sensory neuron where the axon is growing out from the cell body. Activation of those voltage-gated channels produces an action potential that can then propagate along the axons of the first cranial nerve into the olfactory bulb. One experience that I think is common to all of us is the idea of adaptation of our sense of smell. We all know that if we are in an environment where we encounter a particularly strong odor, over the course of the next few minutes, our perception of that odor seems to be much less noticeable to us. While this is a complex phenomenon, sensory adaptation has multiple levels to it. One level is at the operation of the sensory neuron in the periphery, but there are also central mechanisms of adaptation. I want to highlight one known mechanism of adaptation that operates here in the olfactory sensory neuron. As calcium enters the cell, it can interact with calmodulin and produce additional downstream effects. One downstream effect of an interaction of calcium and calmodulin is an impact on this cyclic AMP-gated cation channel. The interaction of calcium and calmodulin can actually reduce the sensitivity of this channel to the binding of cyclic AMP, and this has in effect then a negative feedback signal that is integrated at the level of this cyclic AMP-gated channel, reducing further influx of sodium and calcium, thereby reducing the depolarization with the persistent presence of that particular odorant that's driving this cell's response. Another mechanism of adaptation has to do with this exchanger that we find in the membrane of the cilia. So this is an exchanger that brings sodium ions into the cell and calcium out. So as calcium is exchanged into the extracellular fluids, then that has the effect of downregulating the interaction of calcium with calmodulin. This too contributes to the adaptation of this olfactory receptor neuron to the persistent presence of an odorant. Well, next I'd like to talk about the interactions between odorants and receptors, and this will help us understand a bit of the logic for coding that we find both in the olfactory periphery and also within central structures within the ventral medial forebrain. So what we know are that humans are sensitive to an enormous range of odorants, and odorants come in all kinds of molecular shapes and sizes. And these shapes and sizes interact with a large number of olfactory receptors. In fact, the genes that encode olfactory receptors are among the largest gene families that we know about within vertebrate and even invertebrate systems. So there is tremendous conservation of these genes, but also tremendous diversity. In our case, we've got probably about 1,200 olfactory receptor genes. Most of them are pseudogenes, that is, they don't express a competent protein that functions as an olfactory receptor. The actual number of true genes for olfactory receptors in us is about 400 or so, which is maybe about a third the number that might be present in a typical canine. And perhaps this has a great deal to do with the relative sensitivity of olfactory discrimination and detection in canines versus humans. So humans can be sensitive to odorants down to a concentration range of nanomolar. So that's really a remarkable amount of sensitivity, even though we don't typically think as humans as being the champions in the animal kingdom in olfactory sense. Yet we're definitely holding our own relative to our mammalian kindred. And it's really fascinating to consider how these odorants interact with these receptors. So there can be very small and subtle changes in the molecular structure of an odorant that can give rise to very different percepts. So we want to understand some of the logic as to how that happens. For example, the D isoform of the odorant carvone for many of us smells like rye, whereas the L isoform of carvone smells like spearmint. Very different perceptual qualities with a subtle rotation of a carbon bond in this molecule. Another interesting aspect of olfaction is that the quality of the odor is sometimes modulated by the concentration of the odorant. So for example, low concentrations of the odorant indole smells like flowers, a floral bouquet, whereas high concentrations of the very same odorant molecule can smell quite putrid, what we might think of as exactly the opposite end of this perceptual spectrum. And lastly, I would make the point that most natural odors, they're really not a single odorant, but they're quite complex, much in the way we talked about human speech being spectrally complex, being composed of many fundamental frequencies. In an analogous way, most odorants are quite complex. There are many different odorant molecules that are present within that odor, and these molecules will interact with odorant receptors in various ways. And it's to those interactions that I'd like to turn our attention now using the slide that's before you. So what we have is an example of a combinatorial code that relates odorants to olfactory receptors, and this code is based on the molecular shape of the odorant. Now, this figure, provided by my colleague here at Duke, Hiro Matsunami, illustrates for us the relationship between molecular shape and odorant receptor. For example, this odorant here at the top, it has sort of a triangular shape on the left-hand side of this molecule and a rectangular shape to the right. Well, the rectangular part would appear to fit nicely into a receptor that has a rectangular shaped receptor motif, whereas the triangular piece would appear to fit quite nicely into a molecule that is configured in a way to interact with this triangular shape. Well, of course, the molecules themselves aren't really rectangles or triangles, but rather there is a molecular shape that is interacting with the particular receptive motif that's present in the receptor protein itself. And the point here is that the same odorant molecule can interact with more than one receptor, depending upon the geometrical configuration of odorant molecule and receptor. In the case of this first odorant that is illustrated in this schematic here, we see that this one odorant can interact with at least two different olfactory receptors. For example, we see the complex shape of the odorant to the bottom has molecular form and structure to it that allows it to interact with three different odorant receptors. So what we mean by combinatorial code is a code based on the number and, as it turns out, the location of odorant receptors that interact with the same odorant molecule. So in this scheme, the first odorant would be indicated by the activation of these two odorant receptors here in the two left-hand columns, whereas the odorant to the bottom would be indicated by activation of the three odorant receptors that are off to the right. Now, this combinatorial code that we find in the relationship of odorants to olfactory receptors is converted into a spatial code that allows for the receptor neurons that express a given olfactory receptor allele to grow their axons and converge on the same pair of glomeruli in the olfactory bulb. So let me explain this anatomy and how this remarkable degree of convergence works. So here's an illustration that shows us our olfactory epithelium, and we see a population of olfactory receptor neurons that grow their axons through the cribriform plate and they reach the olfactory bulb. What we find in the olfactory bulb is a really particular compartment that is rich with receptors and synaptic connections between our sensory axons from our olfactory receptor neurons and a variety of postsynaptic targets, including the principal neuron of the olfactory bulb called the mitral cell. So here we see a mitral cell that grows a dendrite into a spherical structure that we call the glomerulus, and it's within that glomerulus that the mitral cell receives synaptic input from an afferent axon. Well, there are a variety of other cell types that are present in the olfactory bulb, namely a small interneuron called the periglomerulus neuron. There's also a small interneuron called the granule cell. Both of these neurons seem to mediate inhibitory interactions within and among glomeruli. There's also a cell called the tufted cell that contributes postsynaptic targets for the afferent input that's arriving in the olfactory bulb. So these spherical structures called glomeruli are the first site of synaptic connection between the olfactory epithelium and the brain. Here's the challenge in setting up this circuitry between the olfactory epithelium and the olfactory bulb. Each glomerulus receives input from about 25,000 olfactory receptor neurons. But what's absolutely astounding about this convergence of information into a single glomerulus is that nearly all of the olfactory receptor neurons that provide input to that same glomerulus will express the very same allele for a particular olfactory receptor. That is, all of these 25,000 neurons are expressing a receptor that will interact with the same set of odorants. This allows for convergence of both anatomy and function into each and every glomerulus that we find in the olfactory bulb. If we look across the entire olfactory epithelium that's present on both sides of the midline, what we find is that all of the olfactory receptor neurons that express the same olfactory receptor grow their axons and converge onto two bilaterally symmetrical glomeruli in the two olfactory bulbs. So this is an example of really a remarkable achievement in pathfinding, whereby axons from a broad epithelial surface will grow and target and ultimately establish synaptic connectivity with a very limited spatial target. In this case, a spatial target of probably less than 100 microns or so of typical dimension. That would be about the diameter of a typical olfactory glomerulus. Now, as I mentioned, there are other cells that contribute to the circuitry of the glomerulus. I won't really say anything more about that except to suggest that the granule cells are a particularly interesting population of neurons. They seem to set up inhibitory networks across the olfactory bulb. They appear to have a role to play in synaptic plasticity that occurs within circuits of the olfactory bulb. And for many mammals, although it's not so clear that it happens in humans, the granule cell population is one set of neurons that is repopulated in life. That is, there is a set of stem cells that produce new neurons that migrate along what's called the rostral migratory stream to enter the olfactory bulb and contribute new neurons to the granule cell layer of the olfactory bulb. Again, we're not so sure whether that really exists in our brains as well as many mammals, but it is curious that of all the populations of neurons in the brain to be supplied throughout adult life, it's the granule cell population of the olfactory bulb in many mammals that benefits from this neurogenesis that occurs even into adult life. We'll say more about development when we come to Unit 5, but just hang on to that thought now, that the olfactory bulb is a recipient of the production of new neurons in many mammals. One last thing about the olfactory bulb before we move on to talk about the olfactory cortex in the brain is that the olfactory bulb seems to solve some of the challenge of having complex odors that contain many different odorants. If we go back for just a moment to the previous slide, where we saw something about the logic of the relationship between odorants to receptors, and we discussed this notion of a combinatorial code, I think it's perhaps apparent to you that the same complex odor might activate quite a large number of olfactory receptor neurons that express each their own allele, but the protein that's produced by that allele, the olfactory receptor, potentially can interact with more than one odorant molecule. And so as a result of this system of combinatorial coding in the olfactory epithelium and the convergence of the sensory neurons to individual glomeruli in the bulb, you might imagine that a complex odor ought to give rise to the activation of tens, perhaps even hundreds of glomeruli in the olfactory bulb. But that often does not seem to be the case. It seems to be that a much more sparse coding mechanism exists in the olfactory bulb for complex odors, which is to say that there seem to be certain glomeruli that might dominate the representation of a complex odor. Not all glomeruli that may be receiving afferent information may be equally activated. And perhaps this is where these additional neurons come into play with lateral inhibitory networks. Much remains to be discovered about how representation in the bulb is actually achieved. But I do think it's notable that there is a sparse coding of complex odors in the activation of only a limited subset of glomeruli. And now the next challenge is to understand how does that information get transferred back into the rest of the ventral medial forebrain, and then how is that information coded and processed, and then ultimately how do these olfactory signals impact behavior. So let's turn now from the bulb. We'll travel down the lateral olfactory tract and consider some of the central processing mechanisms that we find in the olfactory cortex. Well, one of the real puzzles about the physiology of the olfactory system is what happens to this combinatorial code that's established in the olfactory epithelium as odorants interact with their receptors. Well, we've already discussed the principle of the convergence of the axons of olfactory sensory neurons that express the very same allele for an olfactory receptor onto the very same glomeruli in the olfactory bulb. really a remarkable degree of convergence and pathfinding that allows these 25,000 or so olfactory receptor neurons to send inputs to the very same pair of olfactory glomeruli. Well, what about the next layer of processing that we see in the olfactory pathway beyond the olfactory bulb? Well, I'll just remind you of what we talked about near the beginning of this session, that the olfactory bulb sends projections via its mitral cells into a set of targets that we call the olfactory cortex, distributed along the ventral and medial aspects of the forebrain. So here again is our olfactory cortex from the posterior part of the inferior frontal lobe down into the ventral and medial aspects of the temporal lobe. So that's where we find these structures: the piriform cortex, the olfactory tubercle, the amygdala, and the entorhinal cortex, part of the parahippocampal gyrus. Well, what we find in the organization of the projections from the bulb to the olfactory cortex is a broad distribution of afferent terminals to the cortex from any one location in the olfactory bulb. So as a consequence of this, when we present a single odorant to an animal, where this can be studied at the cellular level, what we find is the activation of individual neurons across a wide extent of the olfactory cortex, as if the precise mapping of olfactory receptor neuron to glomerulus in the olfactory bulb somehow has been lost in this widespread distribution of afferents from bulb to cortex. So what we find is that the mitral cells that receive the same input at the same glomerulus will make synaptic connections over a broad extent of the olfactory cortex. Now, with that said, it seems, as best we can ascertain, that there really is no kind of a space map in the olfactory cortex. There's not a map of the olfactory environment that can be easily discerned, nor is there any kind of point-to-point topographic mapping of the olfactory bulb into the olfactory cortex. So in the absence of an obvious spatial representation in the olfactory cortex, one wonders what is the nature of the olfactory code when it comes to cortical processing. And the nature of that code is suggested by the fact that as an animal sniffs and as odorants begin to activate olfactory receptor neurons, what we find is a widespread synchronicity of activity in the olfactory cortex, in this broad extent of ventral medial cortical structures. This suggests that the nature of the olfactory code might actually be temporal rather than spatial, which is to say that the timing of activity across this network may be a means for encoding information that can then be used to make discriminations and appropriate responses to the detection of odorants in the environment. So let's talk now some about the physiological impact of olfactory processing. Well, we've learned quite a bit from studying the anatomy of the olfactory pathways in the brain and the distribution of olfactory information to and through the olfactory cortex. One important point that we've ascertained from a study of this anatomy is that this olfactory cortex, and in particular the piriform cortex, maintains heavy connections with the orbital and medial part of the prefrontal cortex. As I mentioned earlier, this is quite significant for understanding feeding behavior because it's within this orbital and medial part of the prefrontal cortex that the hedonic value of food is represented. In other words, the pleasure and the desirability of consuming food is stamped with a value in the networks of the posterior orbital cortex. It's in this part of the brain where information about smell and taste and texture, perhaps that slight spicy irritation that some of us enjoy in our foods, comes together to produce a pleasurable sensation with the consumption of those foods. So this hedonic value of food is for sure a complex cognitive construct, but it's one that depends upon the confluence of these sensory signals in the posterior part of the orbital cortex. So this is a very important site of integration of olfactory information at a higher level of brain processing. Now, there are also connections from this olfactory cortex to a division of the thalamus called the medial dorsal nucleus of the thalamus. This is a thalamic nucleus that has connections with not only the orbital and medial part of the prefrontal cortex, but really the entire prefrontal cortex. So by this means, olfactory signals can engage a broader network that is used for executive functioning and decision making. Imagine, for example, the behaviors that may be engaged at the detection of a particular odorant. Perhaps it's a smell of a freshly baked pastry or a pie that causes you to wander throughout the home or throughout the neighborhood to that cafe that happens to be the source of that aroma. So there are behavioral choices and there are actions that are being planned and executed based on the acquisition of signals from our olfactory epithelium. Well, that's obviously a very complex example, but it's one that undoubtedly requires this sort of bidirectional engagement of thalamocortical networks. Perhaps you've also had the common experience of a smell evoking a memory. And so it's, again, perhaps not surprising that our olfactory cortex, specifically the entorhinal cortical division, is a preeminent source of inputs into the medial temporal lobe's memory network. And that is found in the hippocampal formation, which is that medial terminus of cortex that folds in upon itself along the medial edge of the temporal lobe. Well, we'll say much more about memory in a later session when we come to Unit 6 near the conclusion of this course. But for now, I'll simply make the point that olfactory signals can be important triggers for the recall of memory. And perhaps this rather immediate access to our memory circuits via this posterior part of the olfactory cortex is one example, or at least one means by which olfactory signals can engage our memory circuits. And lastly, I'll mention that this olfactory cortex, of course, has projections into the hypothalamus, where odorants can engage our visceral motor systems, the output of our autonomic nervous system that can adjust our physiological responses, and the whole host of behaviors that are mediated by circuits in the hypothalamus. Now, in this course, our focus is on human neuroscience. However, if we were taking a more comparative approach, we certainly would spend more time talking about pheromones when it comes to olfaction and the chemical senses. Pheromones are signals that are detected by specializations of the sensory epithelium and the posterior part of the olfactory bulb, where there are transduction mechanisms and processing circuits that are especially tuned to these signals that can have a profound effect on motivated behavior. And these behaviors often are expressed in the context of social communication. Now, there's a specialized organ that receives pheromone signals in many mammals. It's called the vomeronasal organ, and it connects to a special region of the posterior olfactory bulb called the accessory olfactory bulb. In species such as rodents and carnivores, these systems are well developed, and these systems are used to allow chemical messages to mediate complex social behaviors. So these structures are absent in humans. We don't have a vomeronasal organ, neither do we have much, if any, accessory olfactory bulb. So if humans actually respond to pheromone-like signals, they must be doing so through the rest of the olfactory epithelium in what we call the main olfactory bulb, or for us, just our olfactory bulb. This remains a controversial topic. We don't exactly know the nature of these signals that may or may not influence human behavior, but we do have some intriguing examples that perhaps you know about, such as women synchronizing their menstrual cycles when they are housed in dormitory environments. There have been several studies of this phenomenon over the years, as you can imagine, that provide some rather compelling suggestion that perhaps there are indeed something like a pheromone that can modulate, in this case synchronize, reproductive functions in a cohort of people that are housed in a particularly closed, socially confining quarters. Well, that's just one example. There may be others, and there's great interest on the part of commercial enterprises, as you might imagine. Consider the perfume business, for example, wanting to modify behavior based on olfactory cues, as well as other kinds of industries that may want to capture the potential to modify human behavior based on chemical signals. Well, much needs to be done to establish the existence of pheromones in humans, so stay tuned. Perhaps we'll have an answer to this conundrum as research continues to advance over the next decade or so. I'd like to make just a few more points before we leave olfaction and turn to gustation. One of them has to do with the natural decline in olfaction that occurs with age. And here are some data that are replotted for us from our textbook that show really a rather striking and consistent age-related decline in olfactory discrimination ability. Now, this is probably a complex phenomenon that relates both to changes in the olfactory sensory epithelium as well as to central structures in the brain. I think it makes some sense that the olfactory epithelium is particularly vulnerable to infection, to injury, to a variety of sources of trauma and disease. One might imagine the accrual of insult over our decades that would produce a net loss of function as we age. Well, there may also be central mechanisms that are responsible for this that are poorly understood, but it's a very real phenomenon. And it's one that can have a profound impact on, let's say, one's nutritional status, especially in our later years, when food might lose its appeal and our dietary interests may change as a result of this decline in olfaction. So this can be actually quite a serious health-related matter, and it's one that every health professional should understand, especially those that are caring for older adults. Another concern related to olfactory function across our lives is traumatic head injury. Now, I'll remind you that cranial nerve 1 are the axons from the sensory neurons that pass through the cribriform plate in the ethmoid bone to make synaptic connection within the olfactory bulb. Well, unfortunately, when our head is impacted in a traumatic head injury of some sort, there can be a shearing force that might cause the brain to move against the fixed skull. And if there should be some kind of a shearing action of olfactory bulb against the cribriform plate, you can imagine that these very fine axons are at some risk of being severed. Indeed, this is one relatively common consequence of a traumatic head injury, is a loss of olfaction. Now, thankfully, the olfactory sensory neurons are among the very few neurons that we know about that will regenerate throughout life. We think it takes about 2 months or so for a stem cell to differentiate into an olfactory sensory neuron, and then for that neuron to regrow its axon into the olfactory bulb. So there is some recovery of function typically following a traumatic head injury when this type of severance of the first cranial nerve is incurred by a subject. However, often the sense of olfaction, the sense of flavor with the consumption of foods is never quite the same. And I think you can appreciate that if the job of these axons is indeed to find their way back to the glomerulus that is appropriate given the olfactory receptors that any given sensory neuron expresses. One imagines that there are guidance errors and some inappropriate connections that might break down somewhat the coding mechanisms that allow the sensory surface to be mapped into the olfactory bulb. Well, the upshot of all of this is that the first cranial nerve is vulnerable to trauma, and the regeneration of those olfactory sensory neurons and their central axon, while of great benefit in mediating functional recovery, is typically not 100% efficient in finding the exact same synaptic targets that the prior neuron once established. Hence, the nature of olfactory processing is often different, sufficiently different for human subjects to report there being some ongoing variance in their olfactory and flavor perceptions. And just to give you one more look at that olfactory epithelium, I'll again highlight these basal cells, which give rise to a population of precursor cells that can divide and differentiate into olfactory receptor neurons. So here is an indication of a developing olfactory receptor neuron. Its dendrite hasn't quite reached the mucosal surface yet of the olfactory epithelium, but over time, given a few months of development, this olfactory sensory neuron will mature and extend its cilia now from its terminal dendritic bulb out into that epithelium and now function as a fully mature olfactory receptor neuron. Meanwhile, the central process of this developing neuron will make its way back through the cribriform plate, and these axons then will make their way to the olfactory bulb and hopefully with at least some measure of efficiency contact the appropriate glomerulus that will allow any given newly born olfactory sensory neuron to be matched up with the other sensory neurons that express the same olfactory receptor gene allele. Well, I think we're ready to move on from our consideration of olfaction now to talk about the sense of taste, the sense of gustation. So I'll see you soon as we pick up the story of the chemical senses with the story of gustation. Welcome back to our study of the chemical senses, and in this tutorial I'd like to talk to you about the sense of taste, or in more formal terms what we call gustation. So this conversation about our chemical senses again illustrates the complexity of the human brain, and it allows us to once again discover circuitry in the brain that is genetically determined and provides a foundation for function in the central nervous system. And these circuits are modifiable through life experience, and that's a topic we'll get to in more detail when we consider the changing brain in Unit 5. My learning objectives for our discussion on gustation are first to characterize the peripheral and the central organization of the gustatory system. I want us to again focus on the issue of sensory transduction and understand how that occurs within our sensory neurons in our taste buds. And thirdly, I'd like for you to be able to discuss the means by which information is coded within the gustatory system. Well, let's begin with a broad anatomical view of our gustatory pathways. So gustation, or a sense of taste, begins in the oral pharynx, and what we find are sensory cells associated with an anatomical structure that we'll consider in more detail in just a few minutes, called the taste bud. And these taste buds allow for the presentation of ingested molecules. Many of them are water soluble, some of them are lipids, but in any event, they interact with the apical surfaces of our taste cells, where they generate electrical signals through a process of sensory transduction. So we're going to want to understand exactly how that occurs. Well, at the base of these sensory cells, there's a synaptic connection with an afferent axon. And that axon comes from one of three cranial nerves. And so those cranial nerves in question are nerves 7, 9, and 10. So there is a ganglion cell associated with each of these cranial nerves that grows a peripheral axon out to various regions in the oral pharynx where we have taste buds. And as we'll see, these are, of course, on the tongue, as I think you all know, but there are also taste buds on the epiglottis and taste buds that perhaps are even more posterior back in the pharynx. So these axons of cranial nerves 7, 9, and 10 project into the brainstem. And once they are in the brainstem, they synapse with a nucleus of the brainstem that we call the nucleus of the solitary tract. So we're going to want to see this nucleus in just a bit of detail. That nucleus then receives this first order information, and in that nucleus we have cells that grow axons that project from the brainstem on up into the thalamus. So in the thalamus then is where we would find our third order neurons in this pathway. So the nucleus of the solitary tract would be second order, and then the thalamic neurons are the third order. And once again, our thalamic relay is in the ventral and posterior part of the thalamus, but not the exact same cells that we considered when we talked about somatic sensation. For gustation, it's a nearby population of cells in a slightly different part of this broader ventral posterior thalamic complex. But we can just consider this part of the ventral posterior complex of the thalamus. Well, those third order neurons then provide input into the insular cortex. There are probably several zones within the insular cortex that receive this input. So these are regions that we might call primary gustatory cortex, or sometimes we just call them the insular taste regions. Insular taste cortex is how it's labeled in this figure, and then in a more rostral position, the frontal taste cortex, which is really still just part of the insular cortex. As you will recall from our studies of brain anatomy, the insula is that part of the cortex that ends up being folded and covered by the gyrus that forms the upper part of the temporal lobe, and then the gyri that form the lower part of the frontal and parietal lobe, specifically the superior temporal gyrus from the temporal lobe, and from the frontal lobe, the inferior frontal gyrus, the inferior part of the precentral gyrus, and then just a little bit into the parietal lobe, the inferior part of the postcentral gyrus. So this is where we find our taste receptive neurons at the level of the cerebral cortex for the first time in cortical processing. Well, to carry the story onward, I think we'll appeal to a more schematic representation so that you can understand perhaps a little bit more about what happens to this information about taste. So in this schema, we again show our cranial nerves. So here's cranial nerve 7, cranial nerve 9, cranial nerve 10, representing taste buds that are distributed in different parts of the oral pharynx. All of this information converges in the brainstem, in this nucleus of the solitary tract. Well, I'd like to take just a moment and actually show you that nucleus. So if you have your version of Sylvius accessible, you may want to pull that up, or otherwise just follow along here. Well, I've just opened my copy of Sylvius to the Brainstem Atlas. Perhaps you've done the same. And what we're looking for now is the nucleus of the solitary tract. Well, this is a rather long, rod-shaped nucleus that spans the junction of the pons and the medulla. So to find that nucleus, we need to get at the appropriate section. So I'm just going to click down from the level of the midbrain into the pons. So now we're in the upper pons through the middle of the pons, and as we get into the region of the junction between the pons and the medulla, this is actually the upper part of the medulla, what I'm going to be looking for is something that we sometimes describe as a bullseye. That is a dark spot of heavily myelinated fibers surrounded by a lighter region, which would be gray matter. So if we look right in this dorsolateral aspect of the tegmentum of the brainstem, we see something that, well, if you use your imagination, maybe you can imagine this as being something of a bullseye. So if I clear my drawing for just a moment and let Silvius do the work here, this central dark region is what we call the solitary tract. This represents the central process of those first-order afferents that have entered the brainstem through cranial nerves 7, 9, and 10 and are making their way down to the appropriate level of the nucleus. Now, the nucleus actually surrounds the tract. So notice how anatomically this is a bit different than our perhaps more familiar tract and nucleus, which is our spinal trigeminal tract and spinal trigeminal nucleus. In the trigeminal system, the tract is just lateral to the nucleus, which is just medial. But in the solitary system, the tract is completely engulfed by the cells that are receiving the synaptic input from those first-order afferents. Now, there's another important distinction I'd like to make about this nucleus of the solitary tract. There are really two major parts to it. There's a rostral part and a caudal part to this nucleus. The part of this nucleus that is receiving gustatory information is actually the rostral part. So we would encounter this division of the nucleus at roughly this level, the upper part of the medulla, and then on up into the caudal part of the pons, and that's pretty much where we lose it. So we've lost the nucleus now that we are at least a few millimeters into the pons. But as we get very close to the junctional region, now we see this nucleus of the solitary tract, and there's our solitary tract still more or less engulfed by the gray matter. So the rostral part of this nucleus is the gustatory relay. Now there's a caudal part to this nucleus, and if we follow this nucleus down into the medulla just a little bit further, we would continue to follow this for some distance. The caudal part of this nucleus is actually receiving input from the viscera. It's a visceral sensory integrator, and it makes perhaps good sense that our sense of taste would be received in a gray matter structure that also has a caudal division that receives input from our viscera, because taste and visceral sensations are awfully intimately integrated. Imagine experiencing the wonderful flavors of a palatable meal and having those sensations integrated within the sensory signals that are being derived from that gastrointestinal system that does the work of digestion. Well, sometimes it works the other way, right? Sometimes we have a flavor, a gustatory sensation that is signaling the presence of a harmful tastant, a harmful substance that we've just ingested into our mouth. So it's important to get rid of that harmful substance. We do that through various means. We can spit out from our mouth the morsel that we may have just taken in, or if we've already swallowed it, then we actually would benefit from vomiting out that substance. Well, it's as if the nucleus of the solitary tract is a key center for integrating both taste and visceral sensation, and the nucleus of the solitary tract has important outputs to circuits in the brainstem that govern some of these actions, like gagging or coughing or spitting and even vomiting. Well, we'll talk more about our visceral sensory and visceral motor functions when we get deeper into Unit 4, so stay tuned for that. Okay, so just to summarize again this anatomy, the nucleus of the solitary tract is an important integrator of gustatory signals in the rostral division of the nucleus, which is what we're seeing here at this level, whereas the caudal division is an important integrator of visceral sensory signals. Well, I'd like to say just a little bit more about what happens as information is passed from the nucleus of the solitary tract through the thalamus, and then from thalamus up to the cerebral cortex. So when information is processed in our taste regions of the insula, it's integrated with visceral sensory signals that are also processed in this insular cortex. And that information then is passed on to what we might consider to be higher order associational areas, especially in the orbital and medial parts of the prefrontal cortex. And I would highlight one very interesting region of the orbital cortex of the brain. So here's the orbital surface. It's that part of the brain that overlies the orbits of the eyes. Here again is our olfactory bulb and our lateral olfactory tract, just for a little bit of reference. I'd like to draw your attention to this posterior part of the orbital cortex. This, we think, very well may be the first place in the cerebral cortex where flavors are represented. This is a site anatomically that's receiving input from our gustatory pathway, as illustrated in the figure before us. And if you'll recall our discussions about the olfactory pathways, it's also a region that receives input from our primary olfactory cortex, such as our piriform cortex. This is also an area that is going to be integrating signals derived from our trigeminal chemosensory pathways, as well as other higher order information from the somatic sensations associated with feeding. So when we put all that together, what we have is flavor and a sense of the pleasure derived from that food, be it of positive or negative valence. So we talk about the hedonic value of food as being extremely important in reinforcing feeding behaviors. And this perspective on the value of food seems to be represented in this part of the brain, this posterior part of the orbital cortex. Well, information from the cerebral cortex is also passed on into structures like the amygdala, as well as the hypothalamus. And so we can appreciate from this anatomy, I think, how information about the foods we ingest can be distributed to a broad cortical network that's involved in representing the signals derived from inside of our bodies and integrating that with our conscious evaluations and judgments about the significance of these stimuli. Well, we'll talk much more about these topics when we get into the final unit of the course, when we talk about cognition, the associational cortex, and some of the truly fascinating issues in modern neuroscience that revolve around our sense of judgment, our sense of value, our sense of self, and how much of this is derived not just from what we see and what we hear and what we touch in the world that's beyond our fingertips, but also the world within. These sensations, including the chemical sensory signals and our visceral sensory signals that become integrated into our conscious sense of self. So I hope you'll enjoy that discussion. Stay tuned for that. Okay, now I think we're ready to turn our attention to the problem of sensory transduction in the gustatory system. So sensory transduction, again, refers to the challenge of converting mechanical energy, electromagnetic energy, or molecular energy into electrical signals within a nerve cell. So we've seen how that happens in each of the sensory systems, and let's consider now how it occurs in the gustatory system. So I'll just remind you that the tastants, that is the actual molecules that will activate this system, obviously are ingested, taken into the oral pharynx, where they can interact with specializations of the epithelium. We actually find these taste buds in specializations that we call papillae. So at the back of the tongue, we have a row of circumvallate papillae. At the sides of the posterior tongue, we have a set of foliate papillae. And then in the anterior part of the tongue, we have what's called fungiform papillae. And these names are just anatomical terms that describe a bit of the morphology of these papillae. So don't really be concerned with the precise configuration of this tissue that forms these papillae, unless this is of particular interest to you. But otherwise, I just want you to know that there are these papillae that are distributed in different ways across the surfaces of the tongue and then in the posterior part of the oral pharynx. Now, these posterior regions in the esophagus and in the soft palate are going to be innervated probably by branches of the vagus nerve, nerve 10. Here on the tongue, the posterior third of the tongue is going to be innervated by branches of nerve 9, the glossopharyngeal nerve, and the anterior 2/3 or so of the tongue, including these fungiform papillae, these are going to be supplied by branches of cranial nerve 7. Okay, so this accounts for how nerves 7, 9, and 10 provide gustatory signals into that nucleus of the solitary tract of the brainstem. Well, now let's look at the anatomy, the microanatomy of one of these papillae. So what we see is that there's a bit of a trench, so we can imagine that water-soluble tastants work their way into these trenches where they can interact with these taste buds. These specializations that we find in the lateral flanks of these trenches, and it's within those specializations that we find our taste cells. So here's a closer look at a taste bud. So this is the tissue that we find in the tongue. These taste buds include our sensory receptor cells, our taste cells, and they also include a variety of basal cells and supporting cells. Now, the taste cells are the ones that, of course, I would draw your attention to primarily. These are neuroepithelial cells that have an apical surface that comes together into something that we call a taste pore. So it's specifically through this taste pore that our ingested molecules would interact with the apical surface of our taste cells. And it's at that apical surface that interact with the tastant molecules, leading to the depolarization of those taste cells, the release of neurotransmitter at a synapse between the base of the taste cell and the axons of those three cranial nerves, nerve 7, 9, and 10. Okay, so now let's focus in on this apical surface of the taste cell and understand how sensory transduction happens. Well, for a taste cell, sensory transduction happens through a variety of different mechanisms. And as I'll tell you in just a moment, the receptors that are expressed help to define the response of that taste cell. And cells that are tuned for particular molecular forms, thereby giving rise to particular gustatory sensations, are distributed in overlapping but somewhat biased regions over the surface of the tongue and in the posterior part of the oral pharynx. Well, I'll tell you that story in just a moment, but first I want us to focus on the interaction between our tastant molecules that are going to be presented to this taste pore, the apical surface of these taste cells. And we know that there are lots of different flavors out there, right? Well, psychometrically, we can categorize them basically into 5 principal flavors. There are tastant molecules that will induce these flavor perceptions, and those 5 basic categories are salt, acid or sour, sweet, bitter, and just in the last couple of decades, I think psychologists around the world have agreed that there's a 5th category that we call umami. And umami refers to the taste of monosodium glutamate and probably other related amino acids. It's derived from a Japanese word that means delicious. This is probably why some of us enjoy a little bit of monosodium glutamate in our diet. I hope you'll appreciate now that too much monosodium glutamate can be a very bad thing. It can induce excitotoxic injury, but in small amounts, it is sufficient to activate this taste pathway that gives rise to this, apparently for most of us, very pleasurable sensation. Okay, so the point here is that there are different categories of tastants that interact with different taste receptors. And these receptors have quite distinct mechanisms for transducing this information. For the salt and the acids or the sour tastants, they interact with ion channels that have receptors on the extracellular face of these receptors. So when the tastant interacts, an ion channel opens and positively charged cations can enter the cell, depolarize it, and that leads to the activation of voltage-gated channels that ultimately allow for the entrance of calcium at the basal region of the cell, and in a calcium-dependent manner, there's the exocytosis of vesicles that contain the neurotransmitter serotonin. There may be other neurotransmitters involved, but this is one that we know about, and serotonin will interact with receptors expressed at the terminal of that afferent fiber. With sufficient release of neurotransmitter, there will be a depolarization that is sufficient to generate an action potential in that afferent fiber and then communicate the signal on into the central nervous system. Well, other categories of tastants, specifically those tastants that we perceive as being sweet, being bitter, and again this delicious amino acid taste that seems to be distinct in various ways. These tastants interact with G protein coupled receptors. Now, we've talked quite a bit about this category of receptor, so I hope it's now familiar to you. It's a 7-transmembrane protein that is associated on its cytoplasmic surface with G proteins. And these G proteins go on to activate second messenger systems. And these second messenger systems can interact with a variety of other systems within the cell, some of which will lead to the depolarization of the taste cell. Others will release calcium from intracellular stores. So whether calcium is coming in through voltage-gated ion channels or being released from vesicular compartments, the increase in calcium in the basal region of the taste cell is potentially sufficient to lead to the exocytosis of neurotransmitter. So in this particular taste cell, we're illustrating the presence of multiple receptors, and that may be the case. But for many taste cells, there just may be one receptor that is expressed by that taste cell. And this figure gives us more detail than we need to know, but it gives us a closer look at the transduction machinery associated with the receptor. So again, the salts and the acids, they interact with receptors that are on ion channels. And as these receptors are gated, then sodium ions or protons can pass into the taste cell and lead to its depolarization. Other tastants, such as the sweets, the amino acids, the umami tastants, and bitter, interact with G protein coupled receptors. And we know a little bit more about the detail of these G protein coupled receptors. Some of them are monomeric, that is, there's one receptor that interacts with G protein. Some are dimeric, and even heteromeric, meaning that there are different types of receptors. In this case, the TR2, the TR3, or the TR1 and the TR3 that come together to form the functional receptor that interacts with the tastant. In some of these receptor systems, the downstream effector is a TRP channel, specifically a TRPM5 channel that allows for the influx of calcium into the postsynaptic cell, being gated by a second messenger system. In the case of receptors for amino acids and for bitter, we think that second messenger is an IP3 message. So you can see that in various means there are a diversity of mechanisms that allow for the depolarization of the taste cell and the release in a calcium-dependent manner of the neurotransmitter at the basal end of the taste cell. Well, let me say just a little bit more in conclusion as we wrap up this tutorial on the gustatory system about the distribution of these taste receptors across the surface of the tongue. Now, I think we once had a fairly rigid view of the topography of the distribution of taste receptors. We now recognize that there are taste cells that express different taste receptors, and these zones across the surface of the tongue are not absolute. Nevertheless, it remains the case that our taste cells that are especially sensitive to salty tastants tend to be distributed in the anterior and lateral parts of the tongue. The same is true for those receptors that are going to be sensitive to sweet stimuli, as well as the amino acids like monosodium glutamate. Whereas those tastants that are going to interact with receptors for bitter tastes, these tend to be distributed more in the posterior part of the tongue. So we can imagine that salty and sweet would be conveyed primarily by cranial nerve 7, the facial nerve, whereas sensations about bitter will be conveyed by cranial nerve 9. which provides innervation to the posterior third of the tongue. And then finally, our sensations of sour tend to be distributed primarily in the lateral flanks of the tongue. So again, there's a bias in the distribution of these taste cells that express these different receptors, but the bias does not lead to an absolute topography for taste. Well, there's some clinical significance and functional significance here. For example, if you're going to test a patient's sensitivity to taste, you want to make sure that you apply that sweet stimulus to the anterior part of the tongue, the tip of the tongue. If you're testing for the sensitivity to something that we consider bitter, like quinine, for example, you're going to want to make sure that that tastant gets to the posterior part of the tongue. Well, another point that I would make about this topography of the distribution of taste receptors is that receptors in different regions of the tongue, that is, receptors that are sensitive to different kinds of tastants, operate over different concentration regions of those tastants in the ingested food and drink that we consume. And I think there's a good logic to this. So, for example, if we are about to ingest a food that can cause us some harm, it makes quite good sense for our gustatory system, even at the level of sensory transduction, to be especially sensitive to that potentially harmful stimulus. Well, many of the tastants that we might encounter in nature that can do us some harm are those that activate our bitter taste receptors that are found in the posterior part of the tongue. And these receptors are exquisitely sensitive to even very, very small concentrations of tastants in the food and the liquid that we ingest. These tastants are sensitive down to the nanomolar range of sensitivity. So we can very easily detect them in ingested foods, and we can respond appropriately. And that response might involve some kind of integration of gustatory and visceral sensory signals and the production of the appropriate motor act that might involve expelling that substance from our oral pharynx. Now, on the other hand, there are those foods that are not likely to do us so much harm, unless, of course, we ingest them in extremely large quantities. And I'm thinking about salty and especially sweet sensations. And the receptors for these tastants tend to operate in a different dynamic range. Our sensations to sweet and salty tend to be derived with millimolar concentrations of those tastants in the food that we ingest. So I think there's a certain logic here. So substances that do us harm, we're extremely sensitive to with a low threshold for detection, whereas those substances that we might consider to be appropriate nutrients, salts, carbohydrates, sugars, these sorts of compounds we actually need to ingest in sizable amounts to keep our bodies working. Of course, we can abuse that and run into problems with excessive consumption, but the higher detection threshold for salts and for sweets seems to ensure that at least we will consume an adequate supply when that supply is readily available. So we can see that even at the peripheral end of the gustatory system, there is a physiological and adaptive tuning of the sensitivity of our receptor cells for those compounds that will either do us some harm or do us some good. Well, the last topic I'd like to speak about is the coding of information in the gustatory system. So there generally is a proportional relationship to the concentration of the tastant and the activity in the first order axons that enter the brainstem. So coding is based in part on frequency. Coding is also based on the topography of the taste receptors, as is roughly illustrated here in this slide. And this distribution provides the foundation for what we might call a labeled line means of coding. And this means that a certain axon in one of these three cranial nerves is going to be signaling the presence of a particular tastant because of the specializations of the receptor that that axon innervates. And those specializations include what taste receptor is expressed. So obviously, an axon of cranial nerve 7 that supplies the anterior 2/3 of the tongue might supply a sweet receptor, one of those G protein coupled receptors that is tuned for sugar molecules. Well, that labels this axon as representing sweet. So whenever that axon fires an action potential and conveys that signal into the brainstem is now receiving input about the presence of a sweet tastant. So this is what we call a labeled line code. And again, we encountered this concept in the somatic sensory system, and well, to some degree, I think we see evidence of labeled line coding in all of the sensory systems. And again, it refers to the idea that the line or the pathway from peripheral receptor into the brain is labeled based on the presence of particular receptors that accomplish the sensory transduction process. So in this case, we might recognize axons in those cranial nerves that are labeled for the presence of sour, bitter, salty, sweet, and then this amino acid taste that we associate with monosodium glutamate. Well, once this information gets into the central nervous system, it's not yet so clear exactly how it's being processed. So the identity of these tastants seems to be preserved in the relays from the nucleus of the solitary tract into the ventral posterior medial complex of the thalamus, and then up into our taste areas in the insular cortex. But once we get to higher order areas, especially in the orbital cortex of the brain, there really isn't anything that we would recognize as a map of the sensory surface or a map of tastants. Rather, what becomes increasingly important in representation is the hedonic value of the food. That is, do we find this tastant pleasurable, or do we find this tastant producing an aversive response? So at some level of processing, we seem to be less concerned about the identity of the tastant and more concerned about how it impacts motivated behavior. Well, all this talk about the chemical senses is certainly making me hungry, so I think I need to activate a few of my taste cells here, so don't mind me. And I'll see you in a few minutes. We'll talk more about the chemical senses and consider the trigeminal chemosensory system. This is good. I really needed that. Well, welcome to the final component of our tutorial on the chemical senses. And in this part, we come to consider the trigeminal chemosensory system. So we continue to explore the complexity of the human brain through an analysis of some of the circuitry for sensation that's genetically determined and serves as the foundation for sensation, perception, sensory motor integration, and ultimately the behaviors that are stimulated or motivated by our sensory experiences. And we know that the chemical senses can be a very powerful motivator of behavior. What we come to in this part is a consideration of those chemical sensations around the region of the head and inside the head as well that can give rise to some kind of protective or avoidance response. So my learning objectives for this session are that I want you to be able to characterize the general organization of the trigeminal chemosensory system. And secondly, I want you to be able to discuss the sensory transduction mechanisms associated with polymodal C nociceptive fibers. You'll recall that we talked about these kinds of fibers more generally when we considered pain and temperature systems. In this brief segment of our tutorial, I want to focus on those polymodal C fibers associated with the trigeminal nerve that are innervating sensitive tissues in the head that allow us to respond to the presence of an irritating chemical substance in the environment, or perhaps one that we ingest. So I'll just remind you of the distribution of the trigeminal nerve. These sensory axons associated with the trigeminal nerve, cranial nerve 5, have cell bodies in a ganglion that sits in the base of the skull. The sensory axons grow out and innervate a variety of territories in the face and within the head itself. And these branches of the trigeminal are basically organized into three principal divisions. There's an ophthalmic division, which we sometimes consider to be V1, meaning the first or superior division of the trigeminal nerve, nerve 5. There's a maxillary division that we sometimes refer to as V2. And then finally, a mandibular division that we sometimes refer to as V3. So the distribution of these nerves is a bit beyond the scope of this course, so I won't ask you to know in detail their peripheral structures, but I do want you to have a general sense that there is a distribution of the branches of the trigeminal nerve to these different zones of the face. So we can consider the ophthalmic region, the maxillary region, and then the mandibular region. So the ends of the axons that are of concern for us are those that give rise to free nerve endings. So you'll recall that some subset of these axons are going to terminate as free nerve endings, and at the ends of these axonal branches, we will find receptors that are part of this transient receptor potential family of receptors. We call these receptors TRP channels as just a shorthand, so transient receptor potential channels, or TRP for short, and they come in a large variety of specific molecular species that are tuned for particular types of substances in the environment that might activate them. Some are sensitive to heat, to cold, some are sensitive to acids, to protons. Others are sensitive to particular chemicals that might be found in the environment or in substances that we come in contact with or that we might actually ingest. One that's illustrated here is capsaicin. So capsaicin is the substance that is found in many of the hot and spicy foods that many of us actually enjoy consuming. Well, capsaicin can interact with a binding site on the cytoplasmic side of some of these TRP channels and can modulate the currents that then are gated through these channels. So when these channels open, cations like calcium and sodium can enter the terminal end of this free nerve ending, leading to a depolarization, perhaps with the influx of calcium, the activation of second messenger systems that can further modify the response of this polymodal C fiber to the presence of these complex stimuli that might include some of these organic compounds in the foods that we eat or the environments that we come in contact with. So sensory transduction then is about activation of these TRP channels that will lead to depolarization of the terminal membrane and the generation of an action potential and potentially more complex responses within the cell that are mediated by increased levels of calcium. Now I'll just remind you of the central processing of these trigeminal signals. So we're talking about the nociceptive division of the trigeminal nerve and its branches, and these axons then are derived from ganglion cells that send a central process through the trigeminal nerve, which then descends and forms the spinal trigeminal tract. The spinal trigeminal tract then synapses on second-order neurons that are distributed just on the medial side of the tract, called the spinal trigeminal nucleus. And these cells grow an axon that crosses the midline and ascends through the tegmentum of the brainstem in a region nearby the anterolateral system axons. And these second-order pain fibers then terminate in the ventral posterior complex of the thalamus on the medial part of that complex, so our ventral posterior medial nucleus. And the third-order neuron then is the one that relays signals from the thalamus on up to the appropriate location in the cortex. And when we're talking about representation of facial structures, and oral structures, we're talking about the inferior third of the cortex, and even down into that part of the parietal operculum that's buried in the depths of the lateral fissure. Now, this pathway that I've just illustrated for you from peripheral nerve process to cortex will allow our interactions with potentially irritating substances either in our mouths or perhaps on our corneas or in the mucous membranes within our nasal epithelium. These interactions are processed at a conscious level, but they are also integrated at a lower level of processing where appropriate motor responses are triggered in a reflexive sort of way. So, for example, what happens if one were to sniff ammonia salts? Well, a signal would very quickly enter the brainstem, synapse on the appropriate neurons in the spinal trigeminal nucleus. And in addition to the axon that projects on up into the thalamus, there very likely are going to be local collaterals into networks of neurons that we associate with the core of the brainstem, something we call the reticular formation. Some of these neurons will very quickly integrate an appropriate motor response, such as a cough or a sneeze. This is a coordinated visceral and somatic motor response to try to expel the irritating chemical. Well, perhaps the irritating chemical encounters the cornea or the conjunctival tissues around the margins of our globe, our eye. Well, these irritations will likewise enter the brainstem and interact with local circuits that coordinate an appropriate visceral motor response. In the case of corneal irritation, that response would be the tearing up of the surface of the eye. And those tears will be an attempt to dilute and to wash away the presence of this noxious compound that's interacted with these peripheral surfaces. So my point here is that there is a rich set of local connections that engage brainstem circuits that can produce the appropriate visceral motor and somatic motor response that minimizes the damage that potentially might be done through the transduction of one of these potentially irritating chemicals. Well, I'll conclude the chemical senses at this point, and there'll be a study question for you that hopefully will help you integrate some of what you're learning. And otherwise, this is a bit of a juncture for us. We're concluding our survey of the chemical senses, and this will conclude Unit 3 of the course. And we're ready to pivot and take on an understanding of the motor systems that are present within our brain and our spinal cord. So the neurobiological control of movement and motor control is the topic of Unit 4. So I look forward to seeing you on the other side of the Unit 3 quiz as we engage together to explore the motor systems of the brain and spinal cord.